Some nights, you don't need to go anywhere. Some nights, the most restful thing you can do is simply stay. If you're already lying down, already letting the day soften at its edges, this is a quiet place to rest for a while. No urgency, no destination. Just a voice, some science, and the gentle company of one of the oldest creatures this planet has ever quietly kept. If that sounds like something you'd like to stay for, you're welcome here. Only if it feels right. Now, let's drift. There is a beach somewhere tonight. It doesn't matter which one. Maybe it's along the Gulf of Mexico, or somewhere off the coast of Costa Rica, or on a wide and windswept shore in the Indian Ocean. What matters is that the water is dark, and the air is still, and something is moving slowly, almost imperceptibly, up through the shallow foam toward the sand. A sea turtle. She moves the way very old things move. Not lazily, not carelessly, but with a kind of certainty that has nothing to prove. Her flippers pull through the sand in a slow rhythm. Her shell catches what little light exists, and she has been doing this, exactly this, for longer than most of the world's mountain ranges have been standing. Researchers studying the fossil record have found that sea turtles in a form remarkably close to what we see today were present on this Earth somewhere around 220 million years ago. They shared the coastlines with early dinosaurs. They outlasted them entirely. They watched the continents slowly pull apart, the oceans rearrange themselves, ice ages come and recede like quiet tides. And through all of it, the sea turtle changed very little. Scientists sometimes use the phrase living fossil for creatures like this not as an insult, but as a kind of quiet reverence. It means that evolution, which is relentlessly inventive and constantly reshaping life on Earth, looked at the sea turtle and apparently found little reason to revise. Something about the original design was in some deep biological sense already enough. There's something softly reassuring about that idea, that some things don't need to become something else to survive. She reaches the dry sand now, the place where the ocean ends and the land begins, and she stops. She breathes, her movements slow even further. What she is doing at this moment is not instinct in the way we sometimes imagine instinct, a simple mechanical trigger, a switch flipped by temperature or scent. What she is doing is something scientists are still carefully exploring, a form of navigation so precise that it continues to quietly astonish the researchers who study it. Sea turtles, it turns out, can sense the Earth's magnetic field, not in a vague directional way, but with a kind of geographic specificity that functions almost like an internal coordinate system. Studies have indicated that different regions of the ocean carry subtly different magnetic signatures, and that turtles appear to use these differences to locate with remarkable accuracy the specific stretch of beach where they were born, sometimes thousands of miles away. The turtle on this beach tonight may have spent the last 20 or 30 years traveling through the open ocean. She may have crossed entire ocean basins. And yet something in her nervous system, some quiet biological compass we are still learning to understand, brought her back here, to this beach, this particular stretch of sand. Neuroscientists who study animal navigation describe this capacity as a kind of embedded map information that isn't consciously retrieved, but simply known. Not thought about, not reasoned through, just carried the way you carry the shape of a familiar room in your body, even in total darkness. Some researchers suggest that magnetic navigation in turtles is linked to tiny crystalline structures found in their brain tissue minerals that may physically respond to the orientation of magnetic fields. The full mechanism is still being worked out. But the fact of it, the quiet, effortless fact of knowing where you are and where you need to be, that part seems very real. She begins to dig now. Her rear flippers work with surprising precision, scooping and rotating, creating a chamber in the sand that is almost perfectly oval. She doesn't look at what she's doing. She doesn't need to. The body simply knows. And as she digs, it's worth pausing for a moment on something that is easy to overlook. She is not in a hurry. This entire process, the crawl from the water, the selection of a nesting site, the digging, the laying, the covering, the return to the sea, can take several hours. And during none of it does the turtle appear to rush. She doesn't accelerate when something startles her. She doesn't skip steps. She simply continues, at the same pace, with the same deliberate, unhurried rhythm. Scientists who study animal behavior have noted that this slowness is not a limitation. It is, in a meaningful biological sense, a strategy. Sea turtles have a metabolic rate, the speed at which their bodies consume energy, that is dramatically lower than most warm-blooded animals. Their hearts can beat as slowly as 1 beat per minute during certain resting states. Their bodies are extraordinarily efficient at doing what they need to do with the energy they have. What this means in practical terms is a kind of biological longevity that is genuinely remarkable. Sea turtles can live for 70, 80, sometimes over 100 years. Some individuals that researchers have tagged and tracked appear to still be nesting well into their 8th decade of life. The slowness, it seems, is not incidental to their longevity. It may be part of the reason for it. There is a concept in biology sometimes called the rate of living theory, a framework suggesting that organisms with faster metabolisms tend to have shorter lifespans, and those with slower metabolic rhythms tend to persist longer. It's a simplified picture, and biologists will point out many exceptions. But something in the idea holds a quiet logic. That burning slowly means burning longer. The moon has shifted slightly. The beach is the same. She is still digging. And you might find, if you pay attention to your own body right now, that something in you has also slowed. That your breathing has found a slightly longer rhythm. That your thoughts have become a little less sharp-edged, a little more like clouds than like stones. That's not an accident. Researchers in the field of psychoacoustics, the study of how sound and spoken language affect the brain, have found that slow, steady narration in a low vocal register tends to guide the nervous system toward a parasympathetic state, the state associated with rest, digestion, cellular repair, the state your body enters when it understands that nothing right now requires your protection. The brain is always listening for signals, and one of the signals it trusts most is pace. When the pace of what it hears is slow and even, it tends to interpret the environment as safe, which is perhaps why sitting quietly beside something ancient and unhurried, even just in the imagination, has a way of making your own body feel that it can for a moment set something down. She is nearly finished now. Over 100 eggs, each one soft-shelled and warm, have been gently placed in the chamber she made. She will cover them carefully, smooth the sand, and then make her way back to the water. She will not stay to watch over them. Not because she doesn't care, but because this is how it works. The eggs will incubate in the warmth of the sand. The nest will be warmed by the sun over the next several weeks, and the temperature of that warmth will quietly determine something remarkable. Scientists have discovered that the sex of most sea turtle hatchlings is not determined by genetics at the moment of fertilization. It is determined by the temperature of the sand surrounding the nest during incubation. Warmer nests tend to produce females. Cooler nests tend to produce males. A shift of just a few degrees across the incubation period can shift the entire ratio of a clutch. This means that the beach itself, its exposure to sunlight, the depth of the shade nearby, the color and composition of the sand, is quietly making decisions. Not consciously, of course, but in a very real way, the environment is participating in what comes next. Biologists refer to this mechanism as temperature-dependent sex determination, and it is found not only in turtles, but in many reptile species. It is one of the older reproductive systems on the planet, older almost certainly than the one that most mammals, including us, rely on. And it is in some ways deeply intertwined with climate in a way that researchers are now watching very carefully. As ocean temperatures rise and sand temperatures follow, the ratio of female to male hatchlings in some populations has already begun to shift. The Earth is changing. The turtles, as they have always done, are responding to it, slowly, without panic, with nothing but the accumulated wisdom of millions of years of quiet survival. She is back at the water's edge now. A wave comes and takes her, and just like that, she is gone. Back into the dark water, moving more fluidly now, the weight of the land lifting from her. She will swim through the night and the following days and eventually disappear into the open ocean, that vast, largely unmapped interior that she navigates with her invisible compass, her patient body, her extraordinary sense of where she belongs. The nest she left behind sits in the sand, warm and still and unremarkable to anyone who doesn't know to look. And yet inside it, something is already beginning. A process of quiet, unhurried becoming shaped by temperature and time and the slow turning of the earth that will many weeks from now result in dozens of small creatures making their way toward the same ocean, following signals none of us fully understand. There's something worth resting with in that image. The idea that so much of what matters most moves slowly, that the things which endure are often the things that do not rush, that patience in its deepest form is not waiting for something to happen, but moving through the world at exactly the pace that the world was made to accommodate. The turtle doesn't know this, of course. She doesn't think it. She simply lives it. And perhaps that in itself is something worth carrying into the quieter hours. The beach is still. The sand is warm. And somewhere in the dark water, she is already moving toward wherever she needs to be, neck steady, unhurried, and entirely at home in the slowness of things. There is more to her world than a single beach, a single night. The ocean she moves through is full of its own quiet systems, temperatures and currents and ancient rhythms that she navigates without effort, following something her body has always known, but her mind has never needed to name. There is something the body knows before the mind does, a slowing, a quieting, the way breath deepens on its own when the room grows dark, when the sounds of the day finally begin to soften and recede. The body has its own kind of intelligence, older than language, older than thought, and it has been practicing this art of settling for a very long time. Turtles understand this in a way that is almost impossible to put into words, not because they are wise in the way we use that word, but because their bodies have been designed over hundreds of millions of years of quiet, patient evolution to exist in a state that most creatures only visit briefly, a state of profound, unhurried calm. And the biology behind it is in its own way quietly extraordinary. A turtle's metabolism, the inner engine that keeps it alive, runs at a rate so slow that scientists who study it often describe the comparison to other animals as almost difficult to believe. Where a small mammal like a mouse burns through energy rapidly, its heart racing, its breath quick and shallow, a turtle moves through life at an almost geological pace. Researchers have found that the resting metabolic rate of many turtle species is somewhere between 5 and 10 times slower than that of a similarly sized mammal. Some species in the right conditions even slower than that. What this means practically is that a turtle's body requires very little to keep going. A meal that would sustain a turtle for weeks might barely last a mouse a day. The turtle simply needs less. It asks less of the world, and in return, the world seems to offer it more time. The heart at the center of this is worth thinking about for a moment. A resting human heart beats somewhere between 60 and 100 times per minute. Most of us somewhere in the middle of that range, the rhythm so constant and familiar that we rarely notice it at all. A turtle's heart at rest may beat only once every few minutes. Some species during deep winter dormancy beat as infrequently as once every 10 minutes or even less. Just a single, slow, steady pulse. Then quiet. Then another. Scientists who have studied this have found that turtle hearts are structurally adapted to handle long periods between beats. The muscle fibers are different. The electrical signals that trigger each contraction are more patient, more tolerant of waiting. The heart does not race ahead. It simply waits for the right moment. And when it comes, it beats, fully, completely, without hesitation. And then it rests again. There is something almost meditative about that rhythm if you let yourself feel it. Breathing, too, follows a different kind of clock. A turtle at rest may take a breath only once every few minutes, and during dormancy, some species have been observed going without a breath for hours at a time, drawing tiny amounts of oxygen directly through their skin, through specialized tissues near their tail, through the delicate surfaces inside their throat. They have learned over millennia to find other ways of meeting their needs, quieter ways, ways that require less effort, less urgency. Researchers have noted that this capacity for what biologists call cutaneous respiration, breathing through the skin, is one of the reasons turtles can survive conditions that would quickly overwhelm most other animals. Sealed beneath ice for months, submerged in cold, oxygen-poor water, waiting in a burrow for rain that may not come for weeks. The body finds a way. It adapts. It endures. And it does all of this not through strain or resistance, but through a kind of profound physiological acceptance. The body simply adjusts its requirements to match what is available. Cold-blooded, or more precisely ectothermic animals like turtles, do not generate their own body heat the way mammals do. Instead, they borrow warmth from the world around them. Sunlight on a rock, the residual heat stored in dark mud at the edge of a pond, the slow warmth of shallow water on a late afternoon. When warmth is available, their bodies warm and become more active. When the temperature drops, everything slows: the metabolism, the heartbeat, the breath, the movement, until the system settles into a kind of living stillness that is neither sleep nor waking, but something in between. Scientists describe this state as a form of physiological flexibility that most warm-blooded animals simply do not have. Our bodies maintain a constant internal temperature at significant metabolic cost. We burn energy just to stay warm, even when we are doing nothing at all. A turtle, by contrast, allows its internal state to shift with the world around it. It does not fight the cold. It simply becomes, in some sense, a part of it. There is an old idea in certain traditions of contemplative practice, the idea of yielding rather than resisting, of allowing the self to soften and match the shape of whatever surrounds it. Science does not usually use that kind of language, of course. But the biology of the turtle, studied quietly and without agenda, seems to describe something very close to that. The shell itself is part of this story, though perhaps not in the way you might first imagine. Most people think of a turtle's shell as armor, as protection, as a wall between the animal and the world. And it is that, certainly. But it is also something else. The shell is fused to the spine and ribcage of the turtle. It is not a house the turtle carries, but a living part of the turtle itself. The bones have been reshaped over evolutionary time until the shell and the skeleton are one and the same. They cannot be separated. The turtle does not wear its home. It is its home. Researchers studying the evolution of the turtle shell have found evidence suggesting it may have originally developed not for protection from predators, but to help turtles dig, to provide a rigid, stable structure that could be used to burrow efficiently into the earth. The shell as a tool for going inward, for retreat, for finding stillness underground. Only later, it seems, did it become the protective structure we most associate it with today. The thing that keeps the turtle safe came in the beginning from the turtle's instinct to go quiet, to go still, to sink below the surface of the world for a while. There is something quietly worth sitting with in that. When the outside world becomes too much, too hot, too cold, too dry, too dangerous, the turtle draws inward, not in defeat, not in fear, but as a considered biological response. A whole system designed around the idea that sometimes the wisest thing a body can do is simply be still close in and wait for conditions to improve. Scientists have observed that turtles entering this withdrawn state, whether it is estivation in dry heat or the deep cold weather dormancy called brumation, show measurable changes across nearly every system in the body. Heart rate drops, oxygen consumption falls. The digestive system quiets almost entirely. Even cellular processes slow to a fraction of their usual rate. The body is not asleep exactly. It is something more deliberate than that. It is conserving. It is waiting. It is trusting that there will be a time to re-emerge. And there always is. The turtle does not know in any conscious sense that conditions will improve. It does not calculate or plan. Its nervous system is far simpler than ours, built for essential responses rather than complex anticipation. And yet the behavior itself, shaped over hundreds of millions of years of surviving exactly this kind of difficulty, carries a kind of embedded wisdom. The body has learned what the mind could never have reasoned out alone. That rest is not giving up. That stillness is not failure. That waiting in the right circumstances is the most intelligent thing a living system can do. What researchers find remarkable and perhaps a little humbling is how effective this strategy has been. Turtles have outlasted the dinosaurs. They have survived mass extinctions, shifting continents, ice ages, the slow rearrangement of the planet's surface. Not by being the fastest, or the strongest, or the most aggressive, but by being in some essential biological sense extraordinarily good at not overreacting to difficulty. The nervous system of a turtle is not wired for panic. The chemicals that flood a mammal's body in moments of stress, the surge of hormones, the racing pulse, the spike in blood sugar, the heightened alertness, are present in turtles too, but in much smaller quantities, and they clear the system far more slowly, far more gently. The turtle experiences something like stress, but the volume is turned down. The response is proportionate. And then when the source of stress has passed, the system quietly returns to its resting state without drama, without lingering residue. Some neuroscientists who study the stress response across different animal species have noted that the contrast between this kind of measured physiological response and the heightened reactivity common in many mammals raises interesting questions about what optimal stress regulation might actually look like. Not the complete absence of response that would be dangerous, but a kind of calibrated, proportionate reply. A body that notices what is happening, responds appropriately, and then lets it go. The turtle carries no accumulated tension in the way mammals sometimes do. It does not brace against tomorrow. It does not hold in its muscles the memory of last week's alarm. It rests fully without reservation until the next moment calls for something else. And somewhere in that quiet biology, there may be something worth learning. Not a lesson exactly, more like a reminder of something the body already knew before life became complicated, before the hours filled up, before the mind learned to stay awake long after the day was done. The turtle breathes slowly in the dark mud at the bottom of a quiet pond, its heart marking time with patient, unhurried beats. And the night around it holds perfectly still. There is more to this than the shell or the heartbeat or even the long patience of survival. Beneath all of it, beneath the biology and the evolution and the quiet mechanics of a cold-blooded life, there is something in the way a turtle moves through the world that touches on how living things relate to time itself, not just surviving it, but inhabiting it differently, more fully, more slowly, without the constant pressure to be somewhere other than exactly here. And that is where the story moves next, gently, without hurry, into the way that slowness changes not just what the body does, but what the mind is able to notice. Word count approximately 1,800 words, 12 minutes at sleep narration pace. You said banla, chuyen gya, viet kich bantieng anke chuyen khoa. Hok truoch kingu train, ken YouTube, bancho mausak ke chuyen joke, jao hab dan rieng, beat mangjam, de, banla, chuyen gya, viet kich bantieng anke chuyen khoa. Hok truoch kingu train ken YouTube, banko mausak ke chuyen joke jao hab dan rieng, beat mangjam, do ankan han tin tewa sausak. Ban hai viet bang tieng an pan ba, kua kich bandai khoang moy bon foot. Jaila fan ke tiep chung mot video, voi fan train. Jam bao tuan thu theo, kau truk trong file, huang dan viet kich ban ken khoa hok moy. Ma toi jagui theo, phong kach science told. Softly utien trying him thu, gian va chiu sao kam suk hon la, yu to gai kich thikman. Gyong van hin hang cham gan gui truyen, kam hang ko the rat, nan hang fa chu tinte tun hien hu mot kuok tro chuyen luk jem kuya. Noi dung kan dua tren kach du kien, hoa hok go that ko the kiem chung. Moi joan nen juok trien kai theo, dong che du kien, hoa hok jen giai thishne scientists suggest research shows jen lien tuong hoak, and dun he jen ket momem tau, kam giak troi. Ju tile koang, tam moi jen tam moi, lam fantram koa, hok moi, lam jen hai, moi, fantram kam shukva, andu. Kong viet theo kiu giang day, kong ket luan kong pantish nang kong tau kau trao. Tran kam giach kang tang gyun hip ju, emva lien tuch. Ko de thin tuang jat kau hoirat nen hang je gyu suket noi, tun hien voing going he. Kach fan tu so hai jen so moi, hai kan khai that chach kia kan khoa hok khach nau, nan thuk trin ho giach kwan tiem thuk kam shoots ko the ket noi. Kong juok strong lap noi dung jan noi truok jo. Koi fan nai, kan ko joan chuyen tiep tun hien muotma, gyu trang thai, tu gien je tiep tuk sang fan sao, fan tiep thiobat, jaungai sao jo kong dung kach kum hu tomorrow. Chiviet noi dung kong gi tieo je kithuat. Mo jiao lin hoat trang lap kau truch kau. Kong su dung viet tat theo huong dan trong file. Kong chen link kong citation kong hach nguon trong van ban. Du kien khoa hok kan juok dien jat tun hien trong kau chuyen. Han van jadang tun hien hungoi, tat viet tran lap kau trus AI. Gyu pong kach ke chuyen tinte su sak gyaun hip jiu, va kam giak. Hai jam bao noi dung pu hop chin sach YouTube. Hai suing hi kitruok ki viet nheva lu I kong viet, tat theo huong dan trong, file huong dan viet, kich ban ken, khoa hok moin he. Hai jam bao kich ban jat, chat luong chaun hat. No rang hai viet, kich ban jat, moi tren moi giem he. Show more kong kong ba, moi tam Claude responded. Part 3. Slowness changes what you are able to see. Not metaphorically though, perhaps that too, but in a literal, measurable, neurological sense. The speed at which a creature moves through the world shapes in quite direct ways the speed at which its nervous system processes that world. And what emerges from that relationship is something researchers have only begun to fully appreciate in recent decades, that time, as experienced by a living creature, is not fixed. It is not a single river flowing at a steady rate. It is more like water moving through different kinds of landscape, rushing through a narrow canyon in one creature, spreading wide and slow across a quiet delta in another. Turtles occupy one end of that spectrum in a way that is, scientifically speaking, genuinely remarkable. The visual system of a turtle processes information at a rate quite different from our own. Researchers studying the flicker fusion rate of various animals, the speed at which a sequence of separate images blurs into the perception of smooth, continuous motion, have found that slower-moving, lower metabolism animals generally perceive the world at a lower frame rate, so to speak, than faster, higher metabolism ones. A hummingbird, burning through energy at an extraordinary pace, may experience visual time as almost stretched, able to detect rapid movements that would be invisible to us. A turtle, with its slow metabolic engine, perceives a world that is already in some sense smoother, less fractured, less interrupted by the rapid flickering that faster creatures must process and filter. This does not mean the turtle sees less. It may simply mean the turtle sees differently. Researchers suggest that slower visual processing in ectothermic animals is often compensated by heightened sensitivity to other kinds of information. Color discrimination, the detection of subtle movement at the edges of vision, changes in light quality over longer periods of time. A turtle may not notice the quick darting of a nearby insect, but it will notice the slow shift of shadow across a rock that signals a predator approaching from far away. It is tuned, in other words, to a different kind of attention. And attention, the specific texture and pace of it, is one of the most interesting things that neuroscience has been quietly exploring in recent years. We tend to think of attention as something we direct. We point it like a flashlight at whatever we choose to focus on. But researchers have increasingly come to understand that attention is also something that happens to us, that the nervous system is constantly making decisions about what to notice and what to filter out, mostly below the level of conscious awareness. The brain receives an enormous amount of sensory information every second, far more than it could possibly process consciously, and it constructs the experience of the Claude's response was interrupted. Try again. You said ban la chuyen, giaviet kich pantieng an ke chuyen. Khoa hok truoj king utren, ken YouTube, ban ko mau sak ke chuyen, jok jau hap, dan rieng biet mang jam, de, ban la chuyen giaviet kich pantieng an ke chuyen, khoa hok truoj king utren ken YouTube, ban ko mau sak ke chuyen, jok jau hap dan rieng biet mang jam, dau an kan han tin te va sau sak. Ban hai viet bang tieng an pan bon kua kich ban dai kwang moi lam put. Jai la fan ke tiep chung mot video, voi fan tren. Jam bao tuan, tu thio kao tru strong file, huang dan viet kich ban ke, kwa hok moi, ma toi jan gui theo, fong kach science told, softly utien trying him thu gian, chiu sao kam kshukwa, kanang gyu trang thai, ngingoi kua, going he hon la, yutu kich teen man. Fong catch storytelling yongvan, hin hang chamgan gi truyen kam, hang ko the rat, nin hang fa chu tinti tun hien. Noi dung kan dua tren catch du kien, koa hok ko that ko the kiem chung. Moi joan nen juok trien kai theo, dong che du kien, koa hok jen gi I teach. His scientists suggest research shows jen, lien tuong hoak, andun he jen ket mo, mem tau kam giak troi. Giu tile hoang, ta moi jen ta moi, lam fan tram koa, hok moi, lam jen hai, moi, fan tram kam shukva, andu. Kong viet theo kio giang day, kong ket luan kong pan tish nang kong tau kao trao. Tran kam giach kang thang giun hip ju, em valien tuch. Ko te thin tuang jat kao hoirat, nin hang je giu suket noi, tun hien voin going he. Kach pan tu so hai, jen so moi, Hai kan khai that chach kia kan khoa hok khach nau trin ho nhan thuk giach quantium thuk kam shuch ko theket noi. Kong juox trung lap noi, dung jan juox noi, jen hoach juox trien khai trung chach pan truox. Koi fan nai, kan ko joan chuyen tiep tun hien mot magyu trang thai, tu gianje tiep tuk sang fan tiep theo bat jau ngai sao, jonen kong dung kach kum hu, tomorrow. Chi viet noi dung kong kan gi kach tieu je ki thuat. Mo jau lin hoat trang lap chau truts kau. Kong juoch nhat chach tu chuyen tiep nhu, part mot part hai. Kong su dung viet tat theo huang dan trong file, huang dan viet kich ban ken moi. Kong chen link kong sitashen kong juang guon trong van ban. Tu kien koa hok kan juok dien jat, tun hien trong kau chuyen. Lin jong kach joan chuyen, tiep je van fong tun hien kong trong lap. Han van jadang hun goi that viet trang lap kau trux AI. Hoi jam bao noi dung pu hop chin sach YouTube. Hai suing hiki trok, ki viet nheva lu I kong viet, tat theo huang dan trong file. Huang dan viet kich ban ken koa hok moin he. Hai jam bao kich ban jat, chet luong kaun hat. Norang hai viet kich ban jat, moi tren moi jiem. Nhe show more kong kong ba, moi tam Claude responded. Part 4. Part 4 memory is a strange kind of water. It does not stay where you pour it. It seeps through unexpected channels, pools in places you never intended, and sometimes disappears entirely from where you were certain you had left it. Scientists have spent decades trying to understand exactly how living creatures store and retrieve the past, and the more carefully they look, the more it becomes clear that memory is not a recording. It is not a library with fixed shelves and permanent addresses. It is something closer to a living process, one that changes subtly every time it is visited, shaped and reshaped by the present moment, even as it reaches back toward what is gone. Turtles have memory. That much is well established. What is less commonly known is how surprisingly capable that memory appears to be given a nervous system that is, by mammalian standards, quite simple. Researchers studying spatial memory in various turtle species have found that turtles can learn the layout of an environment, a maze, a pond, a stretch of shoreline, with a reliability that suggests something more than basic instinct. They navigate. They return. They remember in some functional sense where food was found, where the water was deeper and cooler, where the sun reached a particular rock at a particular time of day. Box turtles studied in the wild have been found returning to the same small home ranges year after year, not the same general area, but the same specific locations, sometimes within a few meters of where they had been observed many seasons before. Scientists suggest this kind of spatial fidelity relies on a region of the brain called the medial cortex. In reptiles, a structure that is considered an evolutionary precursor to the hippocampus, the area in mammalian brains so closely associated with the formation and retrieval of memories. The turtle's version is simpler, certainly, more modest in its architecture, but it appears to do something functionally similar to build and maintain an internal map of the world, and to use that map to navigate through time as much as through space. What is quietly interesting about this is the question it raises about what memory actually is for. In the conventional understanding, memory serves the future. We remember the past so we can anticipate and prepare for what comes next, so we can learn from experience, avoid earlier mistakes, find again the things that once sustained us. And that is true as far as it goes. But researchers who study memory across a wide range of species have begun to suggest that the picture is more layered than that. Memory, it seems, is also involved in how an organism experiences the present. The internal map that a turtle carries, the accumulated sense of where things are, what to expect, what is familiar, shapes how it moves through the world, right now, in this moment. Familiarity itself is a product of memory. The feeling of being somewhere known, somewhere safe, is memory working quietly in the background without any conscious retrieval at all. There is something almost tender in that idea. The brain, any brain, from the modest cortex of a painted turtle to the vast and complicated architecture of a human mind, is always in some sense carrying its history with it. Not as a burden, but as a kind of orientation. A way of knowing, without having to think, where the ground is solid and where it might give way. In humans, this background operation of memory is something neuroscientists have been mapping with increasing precision. What they have found is that a significant portion of memory processing happens not during the moments of experience themselves, but during rest, during the quiet intervals between activity, during sleep. The sleeping brain is not idle. It is, researchers have found, engaged in a process of remarkable and careful consolidation, replaying the experiences of the day, sorting them, deciding what to strengthen and what to let fade, weaving new information into the existing fabric of long-term memory. The hippocampus and the cortex engage in a kind of slow dialogue during sleep. The hippocampus holding the fresh, fragile impressions of recent experience. The cortex gradually absorbing and integrating them into deeper, more stable structures. This process, which scientists call memory consolidation, appears to be essential. Without adequate sleep, new memories form poorly and fade quickly. The information is there briefly, but it does not take root. What is less often discussed is that this consolidation process is not merely about retention. It is also about meaning. Researchers have found that during sleep, the brain does not simply copy experiences into long-term storage, like files, transferred from one drive to another. It processes them. It connects them to older memories, to emotional associations, to patterns that may not have been visible during waking experience. It looks in some quiet way for what things mean in relation to each other. This is part of why people sometimes wake with a new understanding of a problem they had been struggling with. Why a question that seemed unanswerable at night can feel different in the morning, not because new information arrived, but because the sleeping brain was doing work that the waking mind could not quite manage, making connections, finding the underlying shape of things. Scientists are still exploring the full extent of this nocturnal processing, and there is much that remains genuinely uncertain. But what has become quite clear is that sleep is not a pause in cognitive life. It is a different kind of cognitive life, one that is in certain respects more integrative, more associative, more willing to let things connect in unexpected ways than the focused, directed thinking of waking hours. The turtle, in its long periods of stillness, sunk in cold mud, barely breathing, its heart ticking out its slow and patient rhythm, is not wasting time. Its nervous system, modest as it is, continues its quiet maintenance. Researchers have found evidence that reptiles experience something functionally similar to sleep, including periods of slow wave-like activity in the brain that may serve consolidating functions analogous to those seen in mammals. The biology is different. The scale is different. But the principle that rest is when living systems do their deepest integration work seems to hold across an extraordinary range of creatures. There is something almost reassuring about that consistency. Rest is not a luxury added to the edges of a useful life. It is woven into the center of how living things process and sustain themselves. The turtle knew this in its wordless biological way, long before there were words for knowing anything. And the body knows it too. Your body right now, already beginning its own quiet preparation for the work that only stillness allows. The breath settles a little more. The thoughts lose some of their edges. There is a particular kind of forgetting that happens at the threshold of sleep, not the forgetting of loss, but something gentler, a loosening, a willingness to hold things less tightly. Researchers who study the hypnagogic state, that soft drifting interval between wakefulness and sleep, have noted that it is often characterized by a kind of associative thinking that is different from both ordinary waking cognition and fully formed dreams. Images arrive without being summoned. Connections form between unrelated things. The mind, released from the obligation of directed thought, begins to move in its own slower, more wandering way. Some researchers have suggested that this threshold state may be one of the most creatively fertile moments of the day, a time when the usual filters are lowered, when the mind is willing to follow associations that the waking, goal-directed brain would quickly dismiss as irrelevant. Many people have noted across centuries and cultures that the edges of sleep seem to bring a different quality of understanding. Less sharp, perhaps, but wider. More willing to let unrelated things be related. The turtle drifting in the cold, dark water is not thinking, not in any sense we would recognize, but somewhere in its ancient nervous system, the slow machinery of consolidation and connection is running its quiet programs, integrating the day, maintaining the map, preserving what matters, and releasing what does not. A life simplified to its essentials. And there is a particular quality of peace in that simplicity if you let the idea settle for a moment without reaching for it too eagerly. Memory, after all, is not just what we carry. It is also what we let go. Researchers studying forgetting, once considered simply the failure of memory, have come to understand it as in many ways an active and necessary process. The brain forgets intentionally in the sense that it prioritizes some experiences for consolidation and allows others to fade. Without this, selective forgetting, memory would become overwhelming, cluttered with the irrelevant, crowded with the inconsequential, unable to find the signal within the noise. There is wisdom in release, it turns out, not as a philosophy, as a neuroscience. The turtle carries its shell and its slow heartbeat and its patient map of familiar waters. It does not carry everything. It carries what it needs, and the night continues to deepen around it, soft and without edges, the water holding it perfectly still as the first quiet currents of real rest begin to move through everything, through the mud, through the reeds, through the dark, and the breathing, through whatever it is that lies just beneath the surface of the mind when it finally agrees to let the day go. Something in the nervous system knows how to follow that current if you let it. And the story of how it finds its way, the quiet biological geography of drifting toward rest, is something worth following a little further in its own unhurried time. Slowness changes what you are able to see. This is not a metaphor exactly. It is closer to a biological fact, something researchers who study attention and perception have been quietly documenting for decades in laboratories and in the field, in animals, and in the careful observation of human experience. The pace at which a living thing moves through the world shapes in very direct ways what that world appears to contain. Consider what a turtle actually perceives as it moves along the bottom of a shallow lake or crosses a sun-warmed stretch of earth in the long heat of an afternoon. Its visual system is tuned differently from ours. Turtles have 4 types of color receptors in their eyes. Most humans have 3. This means they can detect wavelengths of light that fall outside what we call visible, including portions of the ultraviolet spectrum. The world as a turtle sees it may contain colors and contrasts and subtle distinctions that human eyes simply cannot register. A flower that looks pale and unremarkable to us might appear vivid, structured, full of navigational information to a turtle moving slowly past it. Researchers who study animal vision have found that the ability to perceive ultraviolet light is more common across the animal kingdom than was once understood. Many birds see it, many insects depend on it, and in turtles, it appears to play a role in finding food, in navigating familiar landscapes, perhaps even in recognizing other members of their own species. The world is richer than any single set of eyes can fully take in. Every creature moves through a slightly different version of it. But what strikes scientists who study turtle perception is not just the range of what turtles can see. It is the relationship between their pace and what they notice. A slow-moving animal by necessity spends more time in any given location. It receives longer, more sustained sensory input from each patch of ground, each shift in light, each change in temperature or smell, or the feel of the surface beneath it. Where a faster animal might receive a rapid sequence of brief impressions, a flicker of information, a judgment, a movement, the turtle accumulates something more layered, more complete. There is a concept in sensory neuroscience, sometimes described as temporal integration, the way the nervous system combines information gathered over a period of time into a coherent perception. The longer the window of integration, the more detail can be included in the final picture. A slow observer, gathering information, patiently has access to a kind of depth that speed simply cannot provide. This may be one of the quiet advantages of a slow life that is easiest to overlook. We tend to associate speed with acuity, with sharpness, with alertness, with intelligence. The fast response, the quick read of a situation. And there is real value in that, of course. But researchers have noted that some of the most nuanced and accurate perceptions that any animal makes come not from rapid reaction, but from sustained, unhurried attention. The kind of looking that takes its time. A turtle navigating its home territory demonstrates a kind of spatial memory and environmental sensitivity that researchers have found surprisingly sophisticated. Studies tracking the movements of various turtle species have shown that individuals return to the same locations year after year, the same nesting beaches, the same basking spots, the same stretches of shallow water where food is reliably found. They do this without maps, without landmarks, in the human sense, navigating by a combination of the Earth's magnetic field, the position of the sun, the chemical signatures of water, the texture and temperature of the ground beneath them. Scientists believe that turtles carry within themselves a kind of internal compass calibrated to the specific magnetic signature of their home, a map written not in images or symbols, but in the felt sense of the planet's own field. Sea turtles famously cross entire ocean basins and return with extraordinary accuracy to the exact beaches where they were born, sometimes after journeys of thousands of miles lasting years. They find their way back, not by following a route they remember, but by following something more fundamental, a felt pull toward a specific place on the surface of the Earth. There is something quietly profound in that. To carry your home, not as a memory, but as a feeling in the body. And this navigation, this whole extraordinary capacity, does not require speed. The turtle does not rush across the ocean to arrive before some deadline. It moves at the pace that its body sets, following the gentle pull of something it has never seen, but has always known, arriving when it arrives, without urgency, without anxiety about the distance remaining. Researchers who study sea turtle migration have noted that the timing of these journeys is regulated by a combination of environmental cues, water temperature, the length of days, the chemistry of the sea itself, rather than any internal clock driven by nervous tension. The turtle does not decide to go. It simply becomes, at the right moment, ready. The body shifts. The orientation changes. and the journey begins quietly and without fanfare from one part of the ocean to another. The sensory world that guides this journey is worth pausing on for a moment. A sea turtle crossing open water relies on inputs that are almost entirely invisible to human awareness. The magnetic field of the Earth, which varies subtly in intensity and inclination across different latitudes and longitudes, creates a kind of invisible grid, a planetary coordinate system that the turtle can read, with structures in its nervous system that researchers are still working to fully understand. There may be magnetite crystals involved, tiny mineral particles that respond to magnetic fields located in the head or along the jaw. The precise mechanism is still being explored, but the sensitivity itself is not in doubt. To navigate by the felt pull of a planetary magnetic field crossing thousands of miles of featureless open water, and to arrive accurately, reliably, generation after generation, at a specific strip of sand on a specific coastline. There is something in that which quiets the analytical mind and asks it simply to receive. Other senses contribute too. Sea turtles detect low-frequency sound through structures in their skulls that transmit vibrations from the water directly into their inner ear, a kind of hearing that is more like feeling a whole-body sense of the acoustic landscape of the ocean. Deep underwater pressure waves, the distant murmur of currents moving against the continental shelf, the subsonic hum of the seafloor. These are not sounds in the way we experience sound exactly. They are more like information arriving through the whole surface of the body at once. Researchers have found that certain sea turtle species can detect the infrasound produced by waves breaking on distant coastlines, frequencies so low that they are completely inaudible to human ears, traveling through water for hundreds of miles before dissipating. The turtle, moving slowly through the open ocean, is listening to shores it has not yet seen, following a sound that is more vibration than noise, a whisper almost from a place it is slowly moving toward. It is worth noticing very gently what this suggests about the relationship between stillness and receptivity. When the body is not consumed by the effort of rapid movement, when the nervous system is not flooded with the demands of speed and reaction, and the constant processing of rapidly changing input, it becomes available for subtler signals. The kind of information that cannot be heard when the environment is too loud, or the movement too fast, or the attention too divided. The kind of perception that requires, in some essential way, a willingness to be still enough to notice. Many meditation traditions have pointed towards something very similar: the idea that beneath the noise of ordinary hurried experience, there is a different quality of awareness available, more expansive, more sensitive to things that move slowly, more able to register the faint, the distant, the almost imperceptible. Science does not usually travel in this territory with great confidence, and researchers are appropriately cautious about drawing direct lines between human contemplative experience and the sensory biology of a reptile moving quietly through ocean water. But the parallel exists, and it is worth holding gently. A turtle, by virtue of its pace, its physiology, and the particular way its nervous system is organized, lives in close and sustained contact with the planet in ways that faster animals often do not. It feels the magnetic field. It hears the infrasonic voice of distant coastlines. It sees colors beyond our range. It knows through the bottoms of its feet and the skin of its underside the temperature and texture of every surface it has ever rested on. Not because it is more intelligent than other animals, but because it has time, because it moves slowly enough that the world has time to speak. And the world, it turns out, has a great deal to say, if anything nearby is willing to be patient enough to hear it. There is something in this that connects very quietly to the experience of a body settling into rest, the gradual slowing, the loosening of the day's accumulated urgency, the way that as the need to react and process and respond begins to ease, other things become perceptible, the weight of the body against whatever it rests on, the rhythm of breath, almost automatic now barely noticed, a sound from outside that would have been invisible an hour ago, a distant something soft and unidentifiable that the settling mind can suddenly just barely hear. The turtle has always known this territory. It lives there quietly and without apology all the time. And from the way the body processes sensation, those slow, layered accumulations of feeling and signal, and knowing there is a natural passage into something else. Something about the way the mind holds what it has perceived, not just in the moment of receiving it, but afterward, in the hours and days that follow, in the deep, patient architecture of what we call memory, and what a turtle, in its own quiet way, might carry as something even older than that. Memory is a strange kind of water. It does not stay where you pour it. It seeps through unexpected channels, pools in places you never intended, and sometimes disappears entirely from where you were certain you had left it. Scientists have spent decades trying to understand exactly how living creatures store and retrieve the past, and the more carefully they look, the more it becomes clear that memory is not a recording. It is not a library with fixed shelves and permanent addresses. It is something closer to a living process, one that changes subtly every time it is visited, shaped and reshaped by the present moment, even as it reaches back toward what is gone. Turtles have memory. That much is well established. What is less commonly known is how surprisingly capable that memory appears to be, given a nervous system that is, by mammalian standards, quite simple. Researchers studying spatial memory in various turtle species have found that turtles can learn the layout of an environment, a maze, a pond, a stretch of shoreline, with a reliability that suggests something more than basic instinct. They navigate, they return. They remember in some functional sense where food was found, where the water was deeper and cooler, where the sun reached a particular rock at a particular time of day. Box turtles studied in the wild have been found returning to the same small home ranges year after year. Not the same general area, but the same specific locations, sometimes within a few meters of where they had been observed many seasons before. Scientists suggest this kind of spatial fidelity relies on a region of the brain called the medial cortex. In reptiles, a structure that is considered an evolutionary precursor to the hippocampus, the area in mammalian brains so closely associated with the formation and retrieval of memories. The turtle's version is simpler, certainly, more modest in its architecture, but it appears to do something functionally similar to build and maintain an internal map of the world, and to use that map to navigate through time as much as through space. What is quietly interesting about this is the question it raises about what memory actually is for. In the conventional understanding, memory serves the future. We remember the past so we can anticipate and prepare for what comes next, so we can learn from experience, avoid earlier mistakes, find again the things that once sustained us. And that is true as far as it goes. But researchers who study memory across a wide range of species have begun to suggest that the picture is more layered than that. Memory, it seems, is also involved in how an organism experiences the present. The internal map that a turtle carries, the accumulated sense of where things are, what to expect, what is familiar, shapes how it moves through the world, right now, in this moment. Familiarity itself is a product of memory. The feeling of being somewhere known, somewhere safe, is memory working quietly in the background, without any conscious retrieval at all. There is something almost tender in that idea. The brain, any brain, from the modest cortex of a painted turtle to the vast and complicated architecture of a human mind, is always in some sense carrying its history with it. Not as a burden, but as a kind of orientation. A way of knowing, without having to think, where the ground is solid and where it might give way. In humans, this background operation of memory is something neuroscientists have been mapping with increasing precision. What they have found is that a significant portion of memory processing happens not during the moments of experience themselves, but during rest, during the quiet intervals between activity, during sleep. The sleeping brain is not idle. It is, researchers have found, engaged in a process of remarkable and careful consolidation, replaying the experiences of the day, sorting them, deciding what to strengthen and what to let fade, weaving new information into the existing fabric of long-term memory. The hippocampus and the cortex engage in a kind of slow dialogue during sleep. The hippocampus holding the fresh, fragile impressions of recent experience, the cortex gradually absorbing and integrating them into deeper, more stable structures. This process, which scientists call memory consolidation, appears to be essential. Without adequate sleep, new memories form poorly and fade quickly. The information is there briefly, but it does not take root. What is less often discussed is that this consolidation process is not merely about retention. It is also about meaning. Researchers have found that during sleep, the brain does not simply copy experiences into long-term storage, like files transferred from one drive to another. It processes them. It connects them to older memories, to emotional associations, to patterns that may not have been visible during waking experience. It looks in some quiet way for what things mean in relation to each other. This is part of why people sometimes wake with a new understanding of a problem they had been struggling with. Why a question that seemed unanswerable at night can feel different in the morning, not because new information arrived, but because the sleeping brain was doing work that the waking mind could not quite manage, making connections, finding the underlying shape of things. Scientists are still exploring the full extent of this nocturnal processing, and there is much that remains genuinely uncertain. But what has become quite clear is that sleep is not a pause in cognitive life. It is a different kind of cognitive life, one that is in certain respects more integrative, more associative, more willing to let things connect in unexpected ways than the focused, directed thinking of waking hours. The turtle, in its long periods of stillness, sunk in cold mud, barely breathing, its heart ticking out its slow and patient rhythm, is not wasting time. Its nervous system, modest as it is, continues its quiet maintenance. Researchers have found evidence that reptiles experience something functionally similar to sleep, including periods of slow wave-like activity in the brain that may serve consolidating functions analogous to those seen in mammals. The biology is different. The scale is different. But the principle that rest is when living systems do their deepest integration work seems to hold across an extraordinary range of creatures. There is something almost reassuring about that consistency. Rest is not a luxury added to the edges of a useful life. It is woven into the center of how living things process and sustain themselves. The turtle knew this in its wordless biological way, long before there were words for knowing anything. And the body knows it too. Your body right now, already beginning its own quiet preparation for the work that only stillness allows. The breath settles a little more. The thoughts lose some of their edges. There is a particular kind of forgetting that happens at the threshold of sleep, not the forgetting of loss, but something gentler, a loosening, a willingness to hold things less tightly. Researchers who study the hypnagogic state, that soft drifting interval between wakefulness and sleep, have noted that it is often characterized by a kind of associative thinking that is different from both ordinary waking cognition and fully formed dreams. Images arrive without being summoned. Connections form between unrelated things. The mind, released from the obligation of directed thought, begins to move in its own slower, more wandering way. Some researchers have suggested that this threshold state may be one of the most creatively fertile moments of the day, a time when the usual filters are lowered, when the mind is willing to follow associations that the waking, goal-directed brain would quickly dismiss as irrelevant. Many people have noted across centuries and cultures that the edges of sleep seem to bring a different quality of understanding. Less sharp, perhaps, but wider, more willing to let unrelated things be related. The turtle drifting in the cold, dark water is not thinking, not in any sense we would recognize, but somewhere in its ancient nervous system, the slow machinery of consolidation and connection is running its quiet programs, integrating the day, maintaining the map, preserving what matters, and releasing what does not. A life simplified to its essentials. And there is a particular quality of peace in that simplicity, if you let the idea settle for a moment without reaching for it too eagerly. Memory, after all, is not just what we carry. It is also what we let go. Researchers studying forgetting, once considered simply the failure of memory, have come to understand it as in many ways an active and necessary process. The brain forgets intentionally in the sense that it prioritizes some experiences for consolidation and allows others to fade. Without this, selective forgetting, memory would become overwhelming, cluttered with the irrelevant, crowded with the inconsequential, unable to find the signal within the noise. There is wisdom in release, it turns out, not as a philosophy, as a neuroscience. The turtle carries its shell and its slow heartbeat and its patient map of familiar waters. It does not carry everything. It carries what it needs, and the night continues to deepen around it, soft and without edges, the water holding it perfectly still as the first quiet currents of real rest begin to move through everything, through the mud, through the reeds, through the dark, and the breathing, through whatever it is that lies just beneath the surface of the mind when it finally agrees to let the day go. Something in the nervous system knows how to follow that current if you let it, and the story of how it finds its way, the quiet biological geography of drifting toward rest, is something worth following a little further in its own unhurried time. The world arrives through the skin before it arrives anywhere else, before the eyes open, before a sound is passed into meaning, before language has anything to say about what is happening. The body is already receiving, already translating the physical world into something the nervous system can use. Touch is, in evolutionary terms, the oldest of the senses, the first, the one that was already present in the earliest forms of animal life, hundreds of millions of years before vision became sophisticated, before hearing developed its fine-tuned machinery, before the brain grew complex enough to name what it was experiencing. And turtles, in this regard, carry something quite ancient within them. The shell of a turtle is not, as many people assume, a structure without feeling. Beneath the outer layer of keratin, the same protein that makes up human fingernails, lies living bone, and beneath that bone, a network of nerve endings that researchers have found to be genuinely sensitive. Turtles can feel pressure on their shells. They can detect vibration transmitted through the shell from the surrounding environment. Some species appear to be sensitive enough to feel the gentle contact of a hand placed on their backs, and researchers studying the sensory capacity of various turtle species have noted behavioral responses that suggest the shell is far more than an insensate wall between the animal and the world. There is something almost poignant about that if you sit with it for a moment. The thing that looks most like armor, the structure that has come to symbolize withdrawal protection, the closing off of the self from what is outside, turns out to be, in its own quiet way, a sensing surface, a way of remaining in contact with the world, even while appearing to be sealed away from it. The skin itself, in all animals, is a remarkable organ. It is the largest organ in the body in terms of surface area, and it contains several distinct types of sensory receptors, each tuned to a different quality of physical experience. Some respond to light touch, others to pressure, some to temperature, others to the particular quality of sensation that the brain interprets as pain. Not pain as punishment, but pain as information, as the body's way of saying that something here requires attention. These receptors send their signals along dedicated nerve pathways to the spinal cord, and from there to various regions of the brain, where the raw data of physical contact becomes experience. What neuroscientists have found, studying how the brain processes touch, is that not all touch is processed the same way. Gentle, slow stroking of the skin at a speed of roughly 1 to 10 centimeters per second activates a specific class of nerve fibers called C-tactile afferents, which appear to be specialized not merely for the detection of contact, but for something more specifically social. For the kind of touch that signals safety, warmth, the presence of another living thing that means no harm. These fibers send their signals to regions of the brain associated with emotion and reward, rather than simply to the areas that map physical sensation. Researchers suggest that this system may be one of the biological foundations of comfort, of the specific calming quality that certain kinds of physical contact carry, distinct from the simple mechanical fact of being touched. The skin knows the difference between information and reassurance, and it has known that difference for a very long time. Turtles, researchers have found, are sensitive to the temperature of their environment in ways that go well beyond simple comfort seeking. Temperature governs almost everything for an ectothermic animal: the speed of digestion, the rate of nerve conduction, the timing of reproduction, the depth of dormancy. A turtle moving from cool water to warm sunlight is not simply seeking comfort in any casual sense. It is actively regulating its physiology, managing its internal chemistry through the deliberate use of external heat. Basking is, in a real biological sense, a form of thermoregulation, and it requires a sensitivity to temperature gradients that researchers have found to be surprisingly precise in many species. Some aquatic turtles can detect temperature differences in the water around them of less than a single degree Celsius, navigating toward the specific thermal conditions that best support whatever biological process is currently most pressing. If digestion is underway, warmth is sought to accelerate the enzymes involved. If the immune system needs activating, a slightly elevated body temperature may be sought in the same deliberate way. The body uses sensation, not just to experience the world, but to manage itself within it. And perhaps that is quietly what sensation is always for. We tend to think of the senses as windows, as the way the outside world gets in. But researchers who study sensory neuroscience increasingly describe perception as something closer to a dialogue. The brain is not passively receiving signals from the world. It is actively predicting what those signals will be based on prior experience, and then updating those predictions when something unexpected arrives. Perception is, in this view, less like watching a live broadcast and more like reading a letter you have already half written yourself and noticing where the incoming words differ from the ones you expected. This is why familiar environments feel different from unfamiliar ones, not just emotionally, but perceptually. The brain has already built a model of a familiar space, and very little new processing is required to navigate it. The senses run more quietly in familiar territory. The nervous system does less work. There is a genuine measurable difference in neural activity between perceiving something known and perceiving something new. And that difference has real physical consequences, including consequences for how alert, how calm, how at ease the body feels within it. The turtle in its home territory, its familiar stretch of pond, its known basking log, its memorized shoreline, is in this neurological sense truly at home. The sensory world it inhabits asks very little of its nervous system, because that system already knows the answers before the questions arrive. The water temperature here, the angle of the light at this time of day, the particular texture of this mud, all of it is already mapped, already expected, already integrated into the quiet background of a body that knows exactly where it is. There is a specific kind of rest that comes from familiarity, not the rest of unconsciousness, but the rest of not having to figure anything out, of moving through a world that has already been understood. Humans feel this too, in their own way. Researchers studying the neural correlates of relaxation have found that environments the brain codes as familiar and safe produce measurable reductions in activity in the amygdala, the region strongly associated with threat detection and the stress response. The familiar bedroom, the particular quality of light through a known window, the sound of rain on a roof that has been known a long time. These things do not merely feel comforting. They are, in a measurable neurological sense, actively calming. The brain's threat monitoring systems quiet down. The body follows. Scent, perhaps more than any other sense, carries this quality of familiarity in its most potent form. The olfactory system, the neural machinery of smell, is like touch, extraordinarily ancient, and it has a structural relationship with the brain that is unlike any other sense, where visual and auditory information travels first to the thalamus, a kind of central relay station, before reaching the cortex. Olfactory signals travel a more direct route, connecting almost immediately to the amygdala and the hippocampus, to the regions most associated with emotion and memory. This is why a scent can carry you without warning and without effort across decades. Why the smell of something familiar can produce in a matter of seconds a quality of feeling that no other sense quite replicates. The neural pathway is shorter. The connection is more direct. The past arrives through smell more quickly and sometimes more completely than through any other door. Turtles have a well-developed sense of smell. Researchers have found that many species use olfactory cues to navigate, to locate food, to find mates, to identify familiar territory. Sea turtles appear to use the chemical signature of their birth beach, its specific mineral composition carried in the water, its distinctive molecular profile, as a navigation anchor when returning to nest, sometimes after decades of open ocean travel. They are following a scent in the broadest sense, back to a place they have not visited since the very beginning of their lives. The body holds onto certain things very quietly and for a very long time. There is a slowness to sensory experience that tends to reveal itself only when the more insistent forms of stimulation are removed. The feeling of sheets against skin, the quality of the dark behind closed eyes, the way the breath sounds heard from the inside. These things are always present. The nervous system is always receiving them, but they only become noticeable when the louder signals have faded. Researchers who study interoception, the sense of the body's own internal state, have found that people vary considerably in how much they naturally attend to these inner signals. The feeling of the heartbeat, the subtle shifts of tension and release in different muscle groups, the quality of the breath. Some people are highly attuned to these signals, others barely notice them at all. But research suggests that gentle attention to interoceptive experience, the kind of soft, non-evaluative awareness of what the body is doing right now, tends to reduce physiological markers of stress and support transitions toward calm. Not trying to change anything, just noticing. Just receiving the way the skin receives the warmth of a familiar room, without effort, without analysis, without needing to decide what it means. The turtle rests on its warm rock, and every nerve ending in its shell is quietly registering the temperature of the afternoon. Not thinking about it, not measuring it against anything, just receiving. The sun moves slowly across the water below. The light changes by degrees so small that they could not be named. And the turtle remains perfectly patiently still, its body in quiet conversation with the world around it, exchanging information so gently that from a distance, nothing seems to be happening at all. But something is always happening in the soft and attentive dark of a body at rest. And that something, the slow, wordless processing that moves through the senses and settles into the deeper layers of the nervous system, has its own quiet rhythm, its own patient way of working through the night, moving closer with each breath toward the particular kind of stillness where the body and the world finally stop distinguishing themselves from each other. Time does not pass the same way for everything that lives within it. That sounds like something a poet might say, standing at the edge of a river at dusk. But it is also quietly and precisely something that science has been demonstrating for several decades now, not as metaphor, but as measurable biological reality. The experience of time, the way it stretches or compresses, the way a single hour can feel like an afternoon or a breath, is not a fixed property of the universe. It is something that happens inside a nervous system. And different nervous systems, shaped by different evolutionary pressures, different metabolic rates, different relationships with the world around them, appear to inhabit time in genuinely different ways. Researchers who study what is sometimes called temporal perception, the way living organisms sense, track, and respond to the passage of time, have found that this capacity is tied in complex ways to metabolic rate, body size, and the speed at which neural signals travel. Smaller, faster metabolizing animals appear to experience time as moving more slowly relative to their own internal pace. A fly processing the world at a rapid neural rate may perceive a human hand moving toward it as something slow enough to react to a fact that explains, at least partly, why flies are so difficult to swat. The world to a creature running on a faster internal clock seems to move more slowly. Turtles sit at the far end of this spectrum. With their slow metabolism, their patient heartbeat, their unhurried neural processing, the world around them may move in some functional biological sense at a relatively faster pace than they themselves do. Not because the turtle is sluggish exactly, but because its internal clock is calibrated to a longer measure, a different denomination of time. Scientists studying circadian rhythms, the internal biological clocks that govern daily cycles of activity and rest, have found that turtles possess these timekeeping systems just as mammals do, though tuned to different parameters. The core molecular machinery of the circadian clock, involving a set of proteins that interact in a feedback loop, cycling roughly every 24 hours, is remarkably conserved across the animal kingdom. The same basic mechanism that tells a turtle when to emerge from the water and bask, when to slow and seek shelter, when to enter its deepest rest, that mechanism shares its fundamental architecture with the one running quietly inside you right now. What changes across species is not the clock itself, but its sensitivity and its relationship to environmental cues. Light is the primary timekeeper for most living things. The presence and absence of light, its quality, its angle, the subtle shift in its wavelength as day moves toward evening provides the environmental signal that keeps internal clocks synchronized with the actual rotation of the planet. In mammals, light enters the eyes and travels along a dedicated neural pathway to a tiny region of the brain called the suprachiasmatic nucleus, a structure roughly the size of a grain of rice that nonetheless serves as the master pacemaker of the entire body's circadian system. From there, signals cascade outward through the nervous system and the endocrine system, coordinating the timing of hundreds of biological processes: hormone release, body temperature, immune activity, digestion, cell repair, so that each happens at the moment in the daily cycle when it is most needed and most efficient. In turtles, the sensitivity to light as a circadian cue appears to be even more direct in some species. Certain turtle species have light-sensitive cells not only in their eyes but in the pineal gland, a small structure deep in the brain that in many reptiles is sometimes called the third eye, not metaphorically but almost literally, as it sits close to the surface of the skull and in some species retains a degree of direct photosensitivity. The turtle is in this sense receiving light information through multiple channels, simultaneously integrating signals about the quality and duration of light from more than one source, building a more complete picture of where it stands in the daily cycle. The body, in its deep and wordless way, always wants to know what time it is, not in any conscious sense, but the systems that regulate almost everything important about how a living body functions: energy availability, alertness, the readiness of the immune system, the chemistry of sleep, all depend on accurate timekeeping. The circadian system is not a convenience. It is infrastructure. Researchers studying what happens when circadian rhythms are disrupted through shift work, through irregular sleep schedules, through prolonged exposure to artificial light at night, have found effects that ripple through the entire biology. Metabolic function changes, inflammatory markers rise, cognitive performance suffers. The mood regulation systems that depend on the predictable cycling of certain neurotransmitters and hormones begin to lose their footing. The body was built to move in rhythm with the light, to rise and become active as the day brightens, and to soften, to slow, to prepare for restoration as the light fades and the dark comes in. And the dark, it turns out, is not simply the absence of light. It is a signal in its own right. When light levels fall in the evening, the pineal gland begins producing melatonin, a hormone that does not force sleep exactly, but that creates the physiological conditions in which sleep becomes easier, more natural, more complete. Body temperature drops slightly, heart rate slows, the digestive system quiets. A gentle, widespread relaxation moves through the body's systems, a biological preparation for the work that only the sleeping hours allow. Melatonin levels peak in the middle of the night and decline gradually toward morning, and researchers have found that this hormonal tide coordinates the timing of many other processes, including some aspects of immune function and cellular repair, so that they occur during the hours of rest when the body's resources are not needed for activity and can be redirected inward. Turtles produce melatonin too. The rhythms differ from ours in their specific parameters, shaped by the different demands of an ectothermic life, but the underlying principle is the same. As the light fades, the chemistry shifts. The body begins its turn inward. The ancient signal runs through the ancient system, and something in the organism responds by becoming quieter, slower, more internal. There is something almost musical about the way this works if you think of it in those terms. Not a melody exactly, more like a long, slow chord that the body holds through the hours of darkness, the sustained note of biological rest, all the systems playing their parts in a quiet coordination that asks for nothing from the conscious mind, that requires no effort or intention, that simply proceeds according to a pattern laid down so long ago that it predates by a vast margin the existence of anything we would recognize as a mind at all. The turtle on the muddy bottom of its winter pond is holding that chord in its own register, heart barely moving, breath suspended, the chemistry of its blood shifting glacially through the long dark of a season that will eventually inevitably turn back toward warmth and light. It is not waiting in any anxious sense. There is no anxiety in it. The biology does not contain that particular frequency. It is simply existing in the manner it was designed to exist within the particular quality of time that this moment offers. And something in that image, the turtle in its cold, patient dark, touches something real in the human nervous system too, when the hour is late and the room is quiet and the day has finally released its hold. The body has its own version of that knowing, its own deep memory of how to do this, how to let the wakefulness thin, how to allow the systems to cycle down, one by one, in their proper order, how to follow the hormonal tide as it moves in its slow, reliable direction. Researchers who study sleep onset have found that the transition from wakefulness into sleep is not a single event, but a gradual process involving the progressive disengagement of different neural circuits, the slowing of electrical activity in the cortex, the withdrawal of consciousness from the world of sensation and thought into a different kind of processing altogether. It takes time. It cannot be rushed, not really any more than the tide can be rushed. The conditions can be invited. The environment can support it. But the process itself unfolds on its own schedule, according to its own biological logic. The turtle understands this without understanding anything. The body moves toward rest, the way water moves toward low ground, not by deciding to, not by effort or intention, but because the conditions are right and the direction is already there, written into the physics of the thing. And perhaps lying here now, in the particular quiet of this hour, the same is true. The light has gone. The melatonin is rising in its slow tide. The temperature of the room is doing its quiet work. The breath is finding its own rhythm without being asked to. The body knows what time it is. It has always known. And what comes next, in this long, slow night, the deepening that happens when time stretches out and the mind begins to move at the pace of something older and more patient than waking thought, that is where the story continues to drift into the wider waters of what the resting brain quietly does with all this dark and all this time. Somewhere beneath the surface of thought, something is always moving. Not the thoughts themselves, the ones with words attached, the ones that arrive with a sense of intention and direction. Something quieter than that. Something that does not announce itself, does not wait to be noticed, and yet shapes, in ways researchers are only beginning to map, almost everything about how a mind navigates the world it finds itself in. The science of unconscious processing is one of the more quietly astonishing fields of modern neuroscience. Not astonishing in the dramatic sense, there are no sudden revelations, no startling reversals of understanding. Just a slow, accumulating body of evidence, suggesting that the vast majority of what the brain does, it does without any conscious awareness whatsoever. Estimates vary, and the question is genuinely difficult to measure with precision, but researchers who study this area suggest that something on the order of 90 to 95% of neural activity occurs beneath the threshold of conscious experience. The mind that we think of as ourselves, the one that deliberates, that chooses, that narrates the ongoing story of a life, is in some measurable sense a small and relatively recent addition to a much older and more extensive system that was already running long before conscious thought arrived on the evolutionary scene. The turtle carries very little of that newer architecture. Its nervous system does not support the kind of reflective, self-aware cognition that generates language and planning and the peculiar human habit of watching oneself think. But the older systems, the ones that process sensory information below the level of awareness, that regulate the body's internal environment, that produce behavioral responses without the intermediate step of conscious decision. Those systems the turtle shares with us in their essential structure across the full distance of our evolutionary separation. And those systems, researchers have found, are doing something quite remarkable all the time. One of the more striking demonstrations of unconscious processing in the human brain involves the way decisions are made. Studies using brain imaging technologies that measure neural activity have found that the neural signatures of a decision, the patterns of activation that correspond to choosing one option over another, can be detected in certain brain regions several seconds before the person becomes consciously aware of having made a choice. The body, in some sense, decides before the mind knows it has decided. The conscious experience of choosing arrives after the fact, like a narrator catching up to events that have already been set in motion. This does not mean that conscious thought is an illusion or that deliberate reasoning plays no role in how we live. Researchers are careful about that interpretation, but it does suggest that the relationship between conscious and unconscious processing is more collaborative, more intertwined than the common intuition of a rational mind in charge of a biological body would suggest. The unconscious is not simply the storage room where unwanted memories are kept. It is an active, ongoing processing system that generates possibilities, evaluates options, integrates information from multiple sources simultaneously, and presents the results to conscious awareness as intuitions, feelings, impulses, and sudden recognitions whose origins are largely invisible. The feeling of knowing something without being able to say how you know it. The sense that a situation is not quite right before any specific evidence has been identified. The unexpected solution that arrives fully formed after a period of not consciously thinking about the problem at all. These are not mysteries or anomalies. They are, researchers suggest, the normal outputs of a processing system that works in parallel with conscious thought on its own schedule, following its own logic. There is something worth sitting with, in that the idea that understanding does not always require effort. That some of the most important processing a mind does happens precisely when the deliberate, directed, effortful kind of thinking steps back and allows the quieter systems room to work. This is one of the reasons researchers who study creativity and problem-solving have found consistently that rest and idle time are not the opposites of productive thought. They are, in many cases, the conditions under which the most integrative, most generative processing takes place. The brain in a state of restful, unfocused awareness, what neuroscientists sometimes call the default mode network. The pattern of neural activity that emerges when the mind is not engaged in a specific external task is not doing nothing. It is doing something quite particular. It is making connections between distant and loosely related ideas. It is running simulations of possible futures. It is processing emotionally significant material that the focused, task-oriented mind did not have bandwidth to address. It is, in a real sense, thinking, just not in the way that thinking usually feels. The default mode network was for a long time considered a kind of neural background noise activity that happened in the absence of anything more important. Researchers who looked more carefully found something quite different. The regions that comprise it areas involved in self-referential thought, in the simulation of other minds, in the integration of past experience with present circumstance and future possibility, are among the most metabolically active in the entire brain during rest. The brain at rest is burning significant energy. It is not resting in the sense of stopping. It is resting in the sense of switching to a different kind of work, one that is perhaps more fundamental to the maintenance of a coherent inner life than the task-focused processing that tends to dominate waking hours. Turtles do not have a default mode network in the mammalian sense. Their nervous systems do not support that kind of elaborate self-referential processing. But the principle of rest, as active reorganization, the idea that periods of reduced external engagement allow internal systems to do their most important maintenance work, seems to hold across a much wider range of biology than the specific architecture of the human brain. During the long dormancy of a winter season, researchers have found evidence of neural reorganization in various reptile species, changes in synaptic connectivity, shifts in the expression of proteins associated with neural maintenance and repair processes that appear to serve functions analogous to some of what happens in the sleeping mammalian brain. The turtle is not simply waiting for the cold to pass. Its nervous system is doing something during that long stillness, something quiet and internal and necessary. There is also something the unconscious does with emotion that deserves a moment of gentle attention. Emotional processing, the way the brain receives, evaluates, responds to, and integrates emotionally significant experience, is to a remarkable degree an unconscious process. The amygdala, which plays a central role in detecting and responding to emotionally relevant stimuli, operates largely below the level of conscious awareness. It can generate a physiological response, a quickening of the heart, a subtle shift in muscle tension, a change in breathing, before the cortex has finished processing what is actually happening. The emotion arrives in the body before it arrives in the mind, in the sense of conscious recognition. Researchers who study this have found that people can have measurable emotional responses to stimuli. They are not consciously aware of having seen images presented too briefly for conscious recognition still produce detectable changes in skin conductance, in heart rate, in the activation patterns of regions associated with emotional response. The emotional system is monitoring the environment, constantly building evaluations and generating responses without waiting for permission from conscious thought. What is interesting about this in the context of rest and sleep is that the emotional processing that the waking mind does not fully complete, the experiences that arrive too quickly or in too concentrated a form to be fully integrated in the moment, continues during rest. Sleep, and particularly the rapid eye movement stages of sleep, appears to be deeply involved in emotional regulation. Researchers have found that adequate sleep is associated with reduced emotional reactivity to stressful stimuli, with greater flexibility in emotional response, with a kind of metabolizing of difficult experiences that leaves them less sharp, less urgent, more integrated into the broader fabric of a life, rather than standing apart from it as unfinished business. The expression of sleeping on something, waiting for the feeling to settle before responding, has a genuine biological basis. The sleeping brain is working on the emotional residue of the day in ways that the waking brain occupied with the demands of the present simply cannot. And this quiet work, this patient invisible processing that happens in the dark and the stillness, is perhaps one of the deepest reasons that rest matters as much as it does, not just for the body, not just for the consolidation of factual memory, but for the ongoing project of remaining in the fullest sense oneself, of staying emotionally coherent, flexible, capable of responding to the world with something other than pure reactivity. The turtle in its winter mud is not processing complex emotions, but it is resting in a way that allows its nervous system to maintain itself, to do the slow and necessary work of biological housekeeping that can only be done in stillness. And in that, there is something quietly parallel to what the human body and mind need from the dark hours, not dramatic healing, not sudden resolution, but the unhurried, ongoing maintenance of a living system that works best when it is trusted to do its own quiet work. The unconscious does not need to be managed. It does not need instruction or supervision. It needs more than anything the space and the stillness to proceed at its own pace. And that pace, it turns out, in the brain, as in the body, in the nervous system, as in the slow chemistry of a creature built for patience, is almost always slower than we think it needs to be. Slower and quieter. And in that quietness, something is always working. Something that cannot be hurried, cannot be forced, can only be allowed, the way water allows itself to find the low places in the dark, the way the breath allows itself to deepen when there is nothing left to do but breathe. And what the body does with that quiet, what happens in the deepest hours when even the unconscious processing begins to soften and thin towards something simpler, that is where this slow and patient story continues to move deeper into the night. There is a kind of intelligence that lives in the body before it lives anywhere else. Not the intelligence of reasoning or analysis, not the kind that assembles arguments or weighs competing possibilities against each other. Something older and more immediate than that. The intelligence of a hand that adjusts its grip before the mind has registered that the object is slipping. The intelligence of a body that flinches from a sudden movement before the eyes have fully processed what the movement was. The intelligence of a stomach that tightens in the presence of something wrong, even when nothing visible has yet announced that anything is wrong at all. Scientists call this somatic intelligence loosely the wisdom of the body as a sensing and responding system, and it has been a growing area of genuine interest in neuroscience and physiology for the past several decades. What researchers have found, looking carefully, is that the body is not simply a vehicle the mind pilots from above. It is a processing system in its own right, one that gathers information, forms something like assessments, and communicates those assessments upward to conscious awareness through the channels of physical sensation. The gut tightens, the shoulders rise, the breath shortens, the chest opens or closes around whatever it has recognized before the thinking mind has caught up. The vagus nerve is at the center of much of this story, and it is one of the more quietly fascinating structures in the entire body, running from the brainstem down through the neck, branching into the heart and lungs, reaching all the way into the abdomen, where it innervates the stomach, the intestines, and much of the digestive tract. The vagus nerve is the longest cranial nerve in the body, and one of the primary pathways of the parasympathetic nervous system, the division of the autonomic nervous system associated with rest, with digestion, with recovery, with the broad physiological state that researchers sometimes describe as rest and digest, in contrast to the fight-or-flight activation of its counterpart. The vagus nerve carries signals in both directions, from the brain down to the organs, certainly modulating heart rate, regulating digestion, influencing immune activity in the gut. But also, and this is the part that has attracted increasing scientific attention, from the body back up to the brain. Researchers have found that roughly 80% of the fibers in the vagus nerve are afferent, meaning they carry information from the body to the brain rather than the other way around. The body, in other words, is sending far more information upward than the brain is sending down. The gut, the heart, the lungs, these organs are not simply following instructions. They are reporting back. They are participating in an ongoing conversation about the state of the organism, and the brain is, to a significant degree, listening. This is the biological basis of what researchers call the gut-brain axis, the bidirectional communication pathway between the enteric nervous system of the gastrointestinal tract and the central nervous system. The enteric nervous system is sometimes called the second brain, not because it generates complex thought, but because of its sheer neurological sophistication. It contains somewhere in the range of 100 to 500 million neurons, more than the spinal cord, organized into its own complex network capable of local processing and coordination independent of the brain above. It regulates digestion, monitors the chemical environment of the gut, communicates with the immune system, and produces a remarkable range of neurotransmitters, including roughly 90 to 95% of the body's total serotonin, a neurotransmitter most commonly associated with mood regulation, but which plays a broader role in signaling throughout the body. The gut makes serotonin largely for local purposes, for regulating the mechanical movements of digestion. But the fact that the gut is such a significant site of serotonin production has led researchers to explore the connections between gut health, gut microbiome composition, and the kind of mood and emotional regulation that we typically think of as happening exclusively in the brain. The results are still being mapped, and much remains genuinely uncertain. But what has emerged is a picture of the body's emotional and cognitive life as far more distributed, far more embodied than the conventional brain-centered model would suggest. Turtles have a vagus nerve. They have an enteric nervous system. Their physiology, while organized around different metabolic priorities, shares this basic architecture of body-brain communication that researchers are finding to be so central to the emotional and regulatory life of vertebrates. The information that flows between a turtle's gut and its brain is different in content and complexity from what flows in a human nervous system, but the channel itself, the ancient pathway of somatic communication, is the same. And what this means, perhaps, is that the felt sense of the body, the quality of physical experience as information, as a form of knowing, is not a peculiarity of human consciousness. It is something older, something built into the vertebrate body plan, so early in evolutionary history that it predates the development of the cerebral cortex by hundreds of millions of years. There is a researcher whose work has shaped much of the modern understanding of this body-based knowing, a neuroscientist named Antonio Damasio, whose investigations into patients with damage to regions of the brain involved in integrating bodily signals with decision-making led him to propose that emotions in the biological sense are fundamentally somatic processes, that the feelings we experience as emotional states are the conscious perception of body states, that fear is not merely a thought or an interpretation, but a pattern of physical change in the heart, the lungs, the gut, the musculature, the skin, and that the brain's role is in significant part to represent these body states to awareness and to use them as information in the ongoing process of navigating a life. In this view, the body is not the passive recipient of emotional experience. It is the substrate of it. Emotion lives in the tissue as much as in the neurons, and rest-deep, genuine physical rest changes the body state in ways that change the felt sense of everything. The muscles release their accumulated tension in a sequence that researchers have found tends to follow a predictable pattern as the body moves towards sleep, the large muscle groups of the back and shoulders generally releasing before the smaller muscles of the face and hands, the jaw unclenching, the forehead, smoothing, each release registered by the nervous system as a small signal of safety, of completion of the day's demands receding. The body's posture of vigilance slowly dissolves, and as it dissolves, the emotional tone that vigilance carries with it dissolves too. This is not metaphor. It is physiology. The body's posture and the mind's state are in continuous bidirectional relationship, and changes in one produce changes in the other through the same channels of somatic communication that the vagus nerve and its associated systems have been maintaining for hundreds of millions of years. Something like this happens in the turtle too, in its own register. As the temperature drops and the body's systems slow toward dormancy, the muscle tone decreases, the posture settles, the physical tension of active engagement with the world releases gradually into the yielding support of mud and cool water. The body stops holding itself upright and simply rests in whatever holds it. There is no resistance, no residual bracing against what might come next. Just the full weight of a small, ancient body giving itself completely to the support beneath it. It is in a purely physical sense a form of trust, and the nervous system receiving the signals of that release, the dropped heart rate, the slowed breath, the decreased muscle tension, the reduced sensory input, interprets the message as safety, as completion, as permission to do its own kind of letting go. Researchers who study progressive muscle relaxation and body-based approaches to stress reduction have found that deliberately guiding the body through a sequence of tension and release, systematically attending to different muscle groups and allowing them to soften, produces measurable reductions in cortisol in blood pressure, in subjective reports of anxiety and distress. The body, when invited into relaxation through deliberate somatic attention, responds. The nervous system follows. The emotional tone quiets. It works because the communication channel was already there, already open, already waiting to carry exactly this kind of message. The message that says, the ground is solid, the body is held. Nothing is required right now except to be here, in this, and let the night do what the night was made to do. And so the breath deepens a little more with each slow cycle, and the weight of the body settles more completely into whatever lies beneath it. And the signals moving up through the long pathways of the vagus nerve grow quieter and slower and softer, like a conversation in a room where the lamps have been turned down one by one until the darkness is full and the voices are barely there at all. And what remains is less a message than a feeling, the simple, ancient bodily feeling of being for this moment completely at rest. The night holds everything, and in the holding something deeper than thought begins to surface something that belongs not to the waking mind, but to the longer, slower rhythms of a creature simply alive in the dark, breathing in the quiet company of an old and patient world. That is where this drifts next, into the quality of connection that emerges when all the louder things have gone still, and what remains is only this, and only now, and only the soft and continuing dark. Living things do not exist alone, even when they appear to. The turtle resting in the shallow mud, at the edge of a still pond, is at first glance a solitary creature. It does not school like fish. It does not flock or herd or den communally in the way so many other animals do. It moves through its days in a kind of quiet independence that can look from the outside like isolation. But look more carefully, not at the turtle itself, but at the web of relationships it exists within, and a different picture begins to emerge. One that is less about solitude and more about a particular kind of belonging. A belonging that does not require proximity, that does not announce itself, that works instead through the slow and invisible chemistry of an ecosystem that has been practicing interdependence for far longer than any individual within it has been alive. Researchers who study ecological connectivity, the ways that species within a shared environment affect one another, depend on one another, shape one another's possibilities simply by being present, have found that turtles occupy a surprisingly significant role in many of the ecosystems where they live. Not through dramatic or visible action, but through the quiet, ongoing influence of a creature that has been present in a particular place for a very long time. Freshwater turtles moving between water and land, as they do throughout their lives, carry nutrients across the boundary between aquatic and terrestrial environments in ways that matter to both. When they emerge from the water and move through the surrounding vegetation, they transport aquatic organic matter attached to their shells, carried in their digestive systems, onto land. When they return to the water, they bring terrestrial material with them. Researchers have described this kind of cross-boundary nutrient transport as a form of ecological linkage, a living bridge between two worlds that might otherwise exchange far less. The eggs buried in the soil by nesting females introduce a concentrated pulse of nutrients into the terrestrial environment. Nutrients that, whether or not the eggs hatch, successfully feed the soil organisms. The plant roots the fungi and bacteria that form the invisible foundation of the land ecosystem. A single nesting season from a population of turtles can represent a measurable contribution to the nutrient budget of the surrounding soil. The turtles are giving something to the land simply by being part of it in a way that requires no effort and produces no visible sign. This kind of invisible contribution, the way a single species shapes the chemistry and ecology of the space it inhabits without any apparent intention, is something researchers in ecology have become increasingly attentive to in recent decades. The concept of ecosystem engineers describes species that physically modify the environment in ways that create or maintain habitat for other species. Beavers are the classic example. Their dam building creates wetlands that support entire communities of plants and animals that would not otherwise exist in that landscape. But the engineering does not have to be so dramatic or so visible to be real. A turtle moving through shallow water disturbs the sediment in ways that release nutrients back into the water column, making them available to aquatic plants and the animals that depend on them. A turtle basking on a partially submerged log creates a small microclimate, a warm, exposed surface that may be used by insects, by smaller reptiles, by birds looking for an elevated vantage point. The turtle is not trying to do any of this. It is simply living. And the living, conducted over long periods of time in a particular place, accumulates into something that the ecosystem has come to depend upon. Scientists studying the decline of turtle populations in various parts of the world have found that the removal of turtles from an ecosystem tends to produce cascading effects that are disproportionate to the apparent simplicity of the animal's lifestyle. The nutrient flows shift, the sediment dynamics change, the small habitat modifications that turtles inadvertently created disappear, and the species that depended on them quietly diminish. The turtle's contribution was invisible until it was gone. There is something in this, the idea of a presence that shapes its surroundings, not through force or intention, but simply through the patient, sustained fact of being there, that feels worth turning over slowly in the mind. Connection in the biological world rarely announces itself. It works through chemistry and timing, and the slow accumulation of small effects over long periods of time. The mycorrhizal networks that link the roots of trees in a forest, allowing the exchange of nutrients and chemical signals across distances that no individual tree could bridge. Alone, these networks are invisible, underground, operating according to a logic that has nothing to do with intention or awareness. The trees do not know they are connected. And yet the connection is real, and it matters, and ecosystems that retain these networks function very differently from those that have lost them. Researchers studying these fungal networks have found that trees in a forest are not simply competing for light and water and nutrients as the simpler model of ecological competition would suggest. They are also, through their root fungal connections, sharing resources older, more established trees, appearing to support younger seedlings in conditions of low light carbon, moving through the network from where it is more available to where it is less so. The forest looked at through the lens of this underground connectivity is less a collection of competing individuals and more something closer to a loosely integrated system where the boundaries between one organism and another are genuinely less clear than they appear from the surface. This does not mean trees are conscious of each other or that anything like deliberate care is happening in any sense we would recognize. Researchers are careful about that interpretation, and rightly so. But the functional reality of the connection, the measurable transfer of resources, the demonstrable effects on growth and survival is well established. The forest is more connected, and that connectivity matters more than the surface appearance of separate trees suggests. Something about that quality of hidden connection, the web of relationship that underlies what looks like solitude, the way living things shape and are shaped by each other through channels that require no awareness to be real, feels oddly intimate in the quiet of a late night, because we are connected in that way too. Not through fungal networks though. The human microbiome, the vast community of microorganisms that lives within and upon the human body, creates its own kind of intimate ecological relationship between the human organism and the microbial life it hosts. Researchers have found that the human body contains roughly as many microbial cells as human cells, and that this community of bacteria, archaea, fungi, and viruses plays roles in digestion, immune regulation, and quite possibly in aspects of mood and cognition that scientists are still in the early stages of understanding. The boundary between self and not self, looked at carefully enough, begins to blur in ways that are scientifically verifiable and quietly astonishing. But the connection that feels most relevant here, in this particular hour, is something subtler than microbiology. It is the connection between a body at rest and the physical environment that holds it. The way the weight of a resting body presses into a surface, and that surface in response pushes back with exactly equal force the simple physics of support, of being held, which the nervous system registers not as physics, but as comfort, as safety, as the felt sense of not having to hold oneself up against anything. This is the same message the turtle receives from the mud that surrounds it, from the water that supports it, from the solid ground beneath. The environment is not neutral. It is actively supportive in the literal physical sense, and the nervous system knows this and responds to it and finds in it something that no amount of internal effort can fully replicate. Researchers who study the neuroscience of social connection have found that the physical presence of another living being, even simply the warmth and weight of a body nearby, produces measurable changes in autonomic nervous system activity. Heart rate tends to synchronize between people in close proximity, particularly in conditions of relaxed mutual presence. Breathing patterns show similar tendencies. The nervous systems of living creatures are, it seems, designed to entrain to one another to find a shared rhythm when the conditions for safety and closeness are present. This is something the body does without instruction, without conscious effort. The synchrony emerges from the biology, not from the will, and it suggests that connection, real physiological connection between one living system and another, is not something added to life as a secondary feature. It is woven into the basic operating logic of the nervous system, present at the level where heartbeat and breath are regulated, where the most fundamental parameters of how a body maintains itself are set. The turtle is not lonely. Its nervous system does not generate that particular kind of ache, but it exists within a web of relationship that is as real as any, held by the mud, warmed by the sun, fed by the ecosystems its presence helps to sustain, connected to its environment through 10,000 invisible threads of chemistry and physics and slow mutual influence. All of it happening without urgency, without effort, simply by virtue of being present over a long period of time in a particular place. And here now, the dark is full of the same kind of invisible holding. The weight of the body against its surface, the temperature of the air against the skin, the sound of the breath, heard from the inside in the deep and particular quiet of a room that has grown still. All of it just here, just this. And the question of what it means to be connected, really connected not in the social or emotional sense alone, but in the older, deeper, more biological sense of being part of a world that holds you whether or not you notice it doing. So that question does not need answering tonight. It only needs to be felt lightly, like the warmth that persists in the ground long after the sun has gone, radiating gently upward into the dark that has settled over everything. And from that warmth, from that ground, the story continues to soften and slow, moving now into the place where the body and the night are no longer quite distinct from each other, where the boundary between resting and drifting grows thin as water, and what remains is only the quiet and the dark and the patient, unhurried passage of time. The body has its own calendar, not the kind kept on walls or in phones, not the one that counts forward in neat numbered squares towards some anticipated point. This calendar is written in chemistry, in the slow cycling of hormones and proteins and cellular processes that rise and fall and rise again according to rhythms that were already ancient when the first reptile pulled itself onto a sun-warmed shore and rested there, breathing the Mesozoic air. The body marks time differently from the mind. It thinks in seasons and tides and the long arcs of biological change, rather than in hours and appointments. And when the mind finally grows quiet enough to listen, this older calendar can sometimes be felt a background pulse, steady and undemanding, that has been running all along beneath the noise of the day. Researchers who study chronobiology, the science of biological time, have found that living systems at every scale of organization, from single cells to entire organisms, exhibit rhythmic behavior. Not just the familiar circadian rhythm of the approximately 24-hour day, though that is the most studied and best understood. There are also ultradian rhythms, which cycle multiple times within a single day, the roughly 90-minute cycle of brain activity during sleep, the similar periodicity that researchers have found in alertness and cognitive performance. During waking hours, the cycles of hormone release that occur several times daily with a regularity so precise that they can be used to estimate the time. And there are infradian rhythms cycling more slowly than a day, weekly, monthly, seasonally, shaping the body's biology across longer spans of time in ways that are often below the threshold of conscious awareness. The body is, in this view, not a static system interrupted periodically by change. It is a system of rhythms, nested within rhythms, each oscillating at its own frequency, all of them interacting and influencing each other in patterns of such complexity that researchers describe it as something closer to a symphony than a mechanism. The question for any living body at any moment is less about what state it is in, and more about where it is in the cycle, where all the cycles are simultaneously, and how they are relating to each other at this particular point in time. Turtles, as creatures whose physiology is governed so directly by the temperature and light of the external environment, embody this rhythmic quality in a way that is unusually visible. The annual cycle of a temperate zone turtle is a long, slow oscillation between activity and dormancy, a biological year that might be imagined as a single, very slow breath. The warm months are the inhale, the period of feeding and movement and reproduction, when the metabolism runs at its most active and the animal engages most fully with the world. The cold months are the exhale, the long, still interior season when almost everything slows to a near stop and the body turns its resources inward toward maintenance and survival. Researchers studying this seasonal cycle in turtles have found that it is not simply a response to cold temperatures, as if the body were a mechanism that slows when chilled and quickens when warmed. The biological preparation for dormancy begins well before temperatures drop, significantly triggered by the shortening of daylight detected by the animal's light-sensitive systems, translated into hormonal and metabolic changes that begin preparing the body for its long interior season, weeks before the environmental conditions that will sustain it have fully arrived. The turtle does not wait for the cold to tell it to slow down. It begins the slowing in anticipation. The body reads the quality of the light and acts on what the light is saying about what is coming. There is something in that quality of anticipatory preparation, the body beginning to move toward rest before rest is strictly necessary, trusting the signal of the changing light, rather than waiting for the pressure of the cold that feels quietly relevant. The human body does this too, in its own way. The rise of melatonin in the evening is not simply a response to darkness that has already fully arrived. It begins in the hour or two before sleep, in response to the dimming light, preparing the body for a transition that will not complete for some time yet. The body leans into rest before rest has fully come. It prepares. It trusts the rhythm. And the rhythm, researchers have found, is more robust when it is respected, when the body's anticipatory signals are honored rather than overridden, when the natural slowing that begins in the late evening is allowed to proceed, rather than being interrupted by bright light, by stimulation, by the insistence of a mind that has not yet decided it is time. Body temperature is one of the most reliable markers of where the human body is in its daily cycle, and it follows a pattern of surprising regularity. Core body temperature begins to fall in the early evening, not in response to the ambient temperature of the room, but as part of the body's own circadian programming, an internally generated decline that reaches its lowest point in the hours before dawn and rises again toward morning. This fall in core temperature is part of the biological preparation for sleep. It facilitates the transition into the deeper stages of sleep, and its timing is so consistent that chronobiologists can use it as a precise marker of circadian phase. The body cools itself to sleep in a very real physiological sense. Heat moves from the core toward the periphery. The hands and feet become warmer as blood flow to the skin increases and heat radiates outward, and the core temperature drops by approximately 1 to 1.5 degrees Celsius over the course of the night. Researchers have found that environments that facilitate this heat loss, rooms that are cool rather than warm, bedding that allows rather than traps, the body's own heat dispersion, tend to support better, more consolidated sleep. The turtle in its cold water is in a sense in continuous alignment with this principle. Its body temperature and the temperature of the water around it are always in equilibrium. There is no gap between what the body needs to do and what the environment is offering. The outside world and the inside world are already the same temperature, and in that sameness there is a kind of frictionless settling that no warm-blooded animal working to maintain its internal heat against the cold can quite achieve. Researchers studying what they sometimes call the thermal comfort zone, the range of environmental temperatures within which a body expends the least metabolic energy on temperature regulation, have found that individual variation is significant, but that most people sleep most deeply in environments that are meaningfully cooler than typical daytime comfort temperatures. The body moving toward sleep is moving toward cool, toward the physical conditions that align with its own internal direction. And the breath in those cooler conditions tends to slow, to deepen, to find the long, even rhythm that researchers associate with the kind of parasympathetic dominance, the rest and digest state, the body's own mode of restoration and repair that the night is designed to sustain. Breathing is among all the body's rhythms, the one that sits most unusually at the intersection of the voluntary and the involuntary. It is the only major autonomic function that can be easily and directly influenced by conscious attention, and it is also the only major voluntary action that continues without any conscious attention at all. The breath runs on its own when the mind is elsewhere, and it responds immediately and measurably when the mind turns toward it. This dual nature makes it a kind of bridge, a place where the conscious and the unconscious meet in something both can touch. Researchers studying the effects of slow, controlled breathing on nervous system activity have found that reducing the breathing rate to somewhere around 5 to 6 breath cycles per minute, slower than the typical waking rate of 12 to 20, produces a measurable and rapid shift toward parasympathetic dominance. Heart rate variability increases, which is associated with greater cardiovascular flexibility and resilience. Blood pressure tends to fall slightly. The electroencephalographic activity of the brain shifts toward patterns associated with calm, with reduced arousal, with the kind of diffuse open awareness that sits at the threshold between wakefulness and sleep. The breath moved slowly and deliberately tells the nervous system that everything is safe, that nothing is required right now, that the long, patient rhythm of rest can be trusted. The turtle breathes perhaps once every several minutes in its cold and quiet water. One long breath, and then a stillness that would be alarming to a creature built differently, but is simply the natural tempo of a life calibrated to a different measure of time. And then eventually another breath, unhurried, complete, each one asking nothing of the next. There is a particular quality of time that emerges when breathing slows, a loosening of the grip that the mind tends to keep on the forward edge of each moment, a gentle withdrawal from the habit of anticipating the next thing before the current thing has finished. The present moment expands very slightly in the space that the slowing creates. It becomes less like a point and more like a field wide enough to simply rest in, without needing to be anywhere other than exactly here. Researchers who study contemplative states and the neuroscience of present moment awareness have found that this quality of temporal expansion, the subjective sense that time has slowed or that the present moment has become larger and more spacious, is associated with reduced activity in regions of the brain involved in self-referential processing, in planning, in the mental time travel of remembering and anticipating. The mind, released briefly from its habitual movement between past and future, settles into the present with an ease that has its own particular texture. Less effortful, less defined, more like water than like stone. And from here, from this slow breath, this cool dark, this body finding its own patient rhythm, in the long and quiet night, the story moves into its final hours, into the deepest part of the dark, where the distinction between resting and dissolving grows so thin it can barely be named, and the turtle, and the mud, and the cold water, and the slow turning of the season are all in their different ways simply part of the same long, unhurried night. The body has its own calendar, not the kind kept on walls or in phones, not the one that counts forward in neat numbered squares toward some anticipated point. This calendar is written in chemistry, in the slow cycling of hormones and proteins and cellular processes that rise and fall and rise again according to rhythms that were already ancient when the first reptile pulled itself onto a sun-warmed shore and rested there, breathing the Mesozoic air. The body marks time differently from the mind. It thinks in seasons and tides and the long arcs of biological change, rather than in hours and appointments. And when the mind finally grows quiet enough to listen, this older calendar can sometimes be felt a background pulse, steady and undemanding, that has been running all along beneath the noise of the day. Researchers who study chronobiology, the science of biological time, have found that living systems at every scale of organization, from single cells to entire organisms, exhibit rhythmic behavior. Not just the familiar circadian rhythm of the approximately 24-hour day, though that is the most studied and best understood. There are also ultradian rhythms, which cycle multiple times within a single day, the roughly 90-minute cycle of brain activity during sleep, the similar periodicity that researchers have found in alertness and cognitive performance. During waking hours, the cycles of hormone release that occur several times daily with a regularity so precise that they can be used to estimate the time. And there are infradian rhythms cycling more slowly than a day, weekly, monthly, seasonally, shaping the body's biology across longer spans of time in ways that are often below the threshold of conscious awareness. The body is, in this view, not a static system interrupted periodically by change. It is a system of rhythms, nested within rhythms, each oscillating at its own frequency, all of them interacting and influencing each other in patterns of such complexity that researchers describe it as something closer to a symphony than a mechanism. The question for any living body at any moment is less about what state it is in and more about where it is in the cycle, where all the cycles are simultaneously, and how they are relating to each other at this particular point in time. Turtles, as creatures whose physiology is governed so directly by the temperature and light of the external environment, embody this rhythmic quality in a way that is unusually visible. The annual cycle of a temperate zone turtle is a long, slow oscillation between activity and dormancy, a biological year that might be imagined as a single, very slow breath. The warm months are the inhale, the period of feeding and movement and reproduction, when the metabolism runs at its most active, and the animal engages most fully with the world. The cold months are the exhale, the long, still interior season, when almost everything slows to a near stop, and the body turns its resources inward toward maintenance and survival. Researchers studying this seasonal cycle in turtles have found that it is not simply a response to cold temperatures, as if the body were a mechanism that slows when chilled and quickens when warmed. The biological preparation for dormancy begins well before temperatures drop, significantly triggered by the shortening of daylight detected by the animal's light-sensitive systems, translated into hormonal and metabolic changes that begin preparing the body for its long interior season, weeks before the environmental conditions that will sustain it have fully arrived. The turtle does not wait for the cold to tell it to slow down. It begins the slowing in anticipation. The body reads the quality of the light and acts on what the light is saying about what is coming. There is something in that quality of anticipatory preparation, the body beginning to move toward rest, before rest is strictly necessary, trusting the signal of the changing light, rather than waiting for the pressure of the cold that feels quietly relevant. The human body does this too, in its own way. The The rise of melatonin in the evening is not simply a response to darkness that has already fully arrived. It begins in the hour or two before sleep in response to the dimming light, preparing the body for a transition that will not complete for some time yet. The body leans into rest before rest has fully come. It prepares. It trusts the rhythm. And the rhythm, researchers have found, is more robust when it is respected, when the body's anticipatory signals are honored rather than overridden, when the natural slowing that begins in the late evening is allowed to proceed, rather than being interrupted by bright light, by stimulation, by the insistence of a mind that has not yet decided it is time. Body temperature is one of the most reliable markers of where the human body is in its daily cycle, and it follows a pattern of surprising regularity. Core body temperature begins to fall in the early evening, not in response to the ambient temperature of the room, but as part of the body's own circadian programming, an internally generated decline that reaches its lowest point in the hours before dawn and rises again toward morning. This fall in core temperature is part of the biological preparation for sleep. It facilitates the transition into the deeper stages of sleep, and its timing is so consistent that chronobiologists can use it as a precise marker of circadian phase. The body cools itself to sleep in a very real physiological sense. Heat moves from the core toward the periphery. The hands and feet become warmer as blood flow to the skin increases and heat radiates outward, and the core temperature drops by approximately 1 to 1.5 degrees Celsius over the course of the night. Researchers have found that environments that facilitate this heat loss, rooms that are cool rather than warm, bedding that allows rather than traps, the body's own heat dispersion, tend to support better, more consolidated sleep. The turtle in its cold water is in a sense in continuous alignment with this principle. Its body temperature and the temperature of the water around it are always in equilibrium. There is no gap between what the body needs to do and what the environment is offering. The outside world and the inside world are already the same temperature, and in that sameness there is a kind of frictionless settling that no warm-blooded animal working to maintain its internal heat against the cold can quite achieve. Researchers studying what they sometimes call the thermal comfort zone, the range of environmental temperatures within which a body expends the least metabolic energy on temperature regulation, have found that individual variation is significant, but that most people sleep most deeply in environments that are meaningfully cooler than typical daytime comfort temperatures. The body moving toward sleep is moving toward cool, toward the physical conditions that align with its own internal direction. And the breath in those cooler conditions tends to slow, to deepen, to find the long, even rhythm that researchers associate with the kind of parasympathetic dominance, the rest and digest state, the body's own mode of restoration and repair that the night is designed to sustain. Breathing is among all the body's rhythms the one that sits most unusually at the intersection of the voluntary and the involuntary. It is the only major autonomic function that can be easily and directly influenced by conscious attention, and it is also the only major voluntary action that continues without any conscious attention at all. The breath runs on its own when the mind is elsewhere, and it responds immediately and measurably when the mind turns toward it. This dual nature makes it a kind of bridge, a place where the conscious and the unconscious meet in something both can touch. Researchers studying the effects of slow, controlled breathing on nervous system activity have found that reducing the breathing rate to somewhere around 5 to 6 breath cycles per minute, slower than the typical waking rate of 12 to 20, produces a measurable and rapid shift toward parasympathetic dominance. Heart rate variability increases which is associated with greater cardiovascular flexibility and resilience. Blood pressure tends to fall slightly. The electroencephalographic activity of the brain shifts toward patterns associated with calm, with reduced arousal, with the kind of diffuse open awareness that sits at the threshold between wakefulness and sleep. The breath moved slowly and deliberately tells the nervous system that everything is safe, that nothing is required right now, that the long, patient rhythm of rest can be trusted. The turtle breathes perhaps once every several minutes in its cold and quiet water. One long breath, and then a stillness that would be alarming to a creature built differently, but is simply the natural tempo of a life calibrated to a different measure of time. And then eventually, another breath, unhurried, complete, each one asking nothing of the next. There is a particular quality of time that emerges when breathing slows, a loosening of the grip that the mind tends to keep on the forward edge of each moment, a gentle withdrawal from the habit of anticipating the next thing before the current thing has finished. The present moment expands very slightly in the space that the slowing creates. It becomes less like a point and more like a field wide enough to simply rest in without needing to be anywhere other than exactly here. Researchers who study contemplative states and the neuroscience of present moment awareness have found that this quality of temporal expansion, the subjective sense that time has slowed or that the present moment has become larger and more spacious, is associated with reduced activity in regions of the brain involved in self-referential processing, in planning, in the mental time travel of remembering and anticipating. The mind, released briefly from its habitual movement between past and future, settles into the present with an ease that has its own particular texture, less effortful, less defined, more like water than like stone. And from here, from this slow breath, this cool dark, this body finding its own patient rhythm in the long and quiet night, the story moves into its final hours, into the deepest part of the dark, where the distinction between resting and dissolving grows so thin it can barely be named, and the turtle and the mud and the cold water and the slow turning of the season are all in their different ways simply part of the same long, unhurried night. Part 11. Something changes in the deepest hours of the night. Not dramatically, not in any way that announces itself or demands attention. It is more like a shift in the quality of the silence, a deepening that happens so gradually that it is nearly impossible to say when it began, only that at some point the night feels different from how it felt an hour ago, fuller somehow, more complete, as though the world has finally finished putting itself away, and what remains is something that was always there, beneath the motion and the noise, but could only be felt when everything else grew still enough to stop obscuring it. Researchers who study the neuroscience of aging and longevity have found themselves returning again and again to a question that seems simple on the surface, but opens into something considerably more complex the longer it is examined. What actually determines how long a living system remains viable, not just functional, but genuinely alive, in the full sense, capable of responding and adapting and maintaining the intricate chemistry of a living body against the constant pressure of entropy? The answer, it turns out, is not straightforward. It involves genetics, certainly, but it also involves something that researchers have come to call the pace of living, the rate at which a body burns through its biological resources, accumulates cellular damage, and depletes the various repair mechanisms that evolution has built into living systems to counteract that damage. The pace of living hypothesis, as it is sometimes called, proposes that organisms with lower metabolic rates, those that burn through energy more slowly, that generate fewer of the reactive oxygen species that are a byproduct of cellular respiration and a primary driver of cellular aging tend to live longer relative to their body size than faster metabolizing creatures. A small mammal with a rapid metabolism like a mouse may live only a year or two. An animal of similar size but far slower metabolic pace might live decades. The chemistry of living slowly, it seems, is also in significant ways the chemistry of living long. Turtles are among the most striking examples of this principle in the entire animal kingdom. Researchers studying the biology of turtle longevity have found evidence that turtles age in ways that are genuinely unusual among vertebrates. The concept of negligible senescence, the apparent absence of the typical age-related deterioration in physiological function that characterizes aging in most animals, has been observed in several turtle species. Researchers have found that older turtles do not show the expected declines in immune function, reproductive capacity, or cellular repair efficiency that would be anticipated in most other animals of comparable age. Some species appear to maintain stable physiological function for decades beyond what mammalian aging curves would predict for any animal of their size. The Blanding's turtle, a medium-sized freshwater species native to parts of North America, has been studied in detail over several decades by researchers tracking individual animals. What they found was quietly remarkable. Turtles in their 60s and 70s showed no measurable decline in reproductive success compared to much younger individuals. Their immune parameters remained stable. Their activity levels and survival rates did not decrease with age in the way that virtually all other vertebrates experience. The body maintained at this slow and patient metabolic pace appears to resist the ordinary arithmetic of biological time. Scientists are still exploring the precise mechanisms behind this, and there is much that remains genuinely uncertain. Some researchers point to unusually efficient antioxidant systems that may allow turtles to neutralize cellular damage more effectively than faster metabolizing animals. Others focus on the structural integrity of the chromosome ends, the telomeres, which in most animals shorten with each cell division, and whose progressive shortening is associated with cellular aging and eventual dysfunction. In some turtle species, telomere length appears to remain more stable across the lifespan than it does in comparable mammals, though the full picture of why this is the case remains an active area of investigation. What is clear is that the turtle's relationship with time, its particular way of moving through the years at a pace that the rest of the vertebrate world rarely matches, has biological consequences that reach all the way down to the molecular level. The slowness is not incidental, it is structural. It is woven into the chemistry of every cell. And there is something in this that touches very gently on a question that the human mind tends to circle back to in the quiet hours, the question of what a life is, for what it means to have enough time, what it might feel like to be less urgently in a hurry about the whole thing. Not a philosophical question exactly, more like a physical one. A question the body asks in its own way through the quality of the tension it carries or releases, through the rate at which it moves through the hours, and the degree to which it treats each moment as something to be gotten through on the way to the next one. Researchers who study subjective well-being and what psychologists sometimes call the experience of time affluence, the felt sense of having enough time, of not being continuously pressed for it, have found that this quality of psychological spaciousness is not simply a function of how much time a person actually has. It is also perhaps primarily a function of how they relate to the time they have. People who report high levels of time pressure often have objectively similar schedules to those who report feeling relatively unhurried. The difference lies somewhere in the relationship between the person and the passing moment, in whether time feels like a resource being depleted or something more like a medium being inhabited. This is, of course, easier to describe than to practice. The conditions of modern life generate genuine pressures that are not simply matters of perception. And yet the research consistently finds that the experience of time pressure is more malleable than it feels, that certain practices and orientations tend to shift it, at least partially, in the direction of spaciousness. Among them, researchers note, is the practice of giving full attention to whatever is currently happening, not splitting attention between the present task and the accumulating list of what is not yet done, and allowing experiences to unfold at their own pace rather than accelerating them toward their conclusion. The turtle does not practice this. It simply is it. Its nervous system does not generate the forward-leaning urgency that makes a moment feel like an obstacle to the next moment. It does not experience the gap between where it is and where it should be, because it carries no image of where it should be. It simply exists in the pace its biology provides, and that pace for 200 million years of evolutionary history has proven to be exactly sufficient. There is a cellular process that researchers have been studying with increasing interest over the past 2 decades, a process called autophagy, from the Greek meaning something close to self-eating, which refers to the mechanism by which cells break down and recycle their own damaged or dysfunctional components. Rather than allowing old misfolded proteins and damaged organelles to accumulate and interfere with normal cellular function, the cell packages them and dismantles them, recovering the raw materials for new construction. It is a form of internal housekeeping, and it is essential to cellular health. Disruptions in autophagic function are associated with a range of age-related conditions, and researchers studying longevity across species have found that efficient autophagy appears to be a common feature of animals that age more slowly. Autophagy is upregulated, increased by caloric restriction, by fasting, and by sleep. The sleeping body, particularly during the deeper stages of slow-wave sleep, shows increased autophagic activity in neurons and other cell types. The night hours, it turns out, are partly a time of cellular renovation, a period when the accumulated damage of the day's activity is identified and processed and cleared away, making room for the new. What feels like rest from the outside is at the cellular level a carefully organized maintenance program, running its own patient checks through every tissue of the body. The turtle's long dormancy, with its dramatically slowed cellular activity, may serve analogous purposes at a different timescale, a season-long interval of reduced accumulation and systematic internal renewal that allows the body to enter each active period in better biological condition than continuous activity would permit. Rest at every scale, from the daily sleep cycle to the seasonal dormancy of a wintering turtle, appears to be when living systems do their most fundamental maintenance. Not the dramatic repairs, but the quiet, steady, invisible work of keeping everything in order, of clearing away what has accumulated, of maintaining the integrity of the systems that everything else depends upon. And lying here now, in the deepest part of the night, the body is doing exactly this, without instruction, without effort, following a program so ancient and so deeply embedded that it needs nothing from the conscious mind except the willingness to step back and allow it to proceed. The cells are doing their quiet work. The breath is doing its. The heart, steady and unhurried, marks the passage of each slow minute in its own private language of rhythm and rest. And the night, this particular night, with its particular quality of fullness and dark, holds all of it. The turtle in its cold mud, and the body in its warm room, and the million slow processes of maintenance and renewal that are happening right now in every living thing that has found its way to stillness. Researchers have found that the hours between approximately 1 and 4 in the morning represent the period of deepest biological rest in most people, aligned with natural circadian timing, the time when core temperature is lowest, when growth hormone release peaks, when the deepest stages of sleep are most concentrated, when the brain performs its most thorough clearance of the metabolic byproducts that accumulate during waking hours. The glymphatic system, a network of channels surrounding the brain's blood vessels that become significantly more active during sleep and appears to serve a cleansing function, flushing waste products out of the brain tissue and into circulation. For removal operates most efficiently during these deep, still hours. The brain, in other words, literally cleans itself during sleep. The fluid that bathes the neural tissue moves more freely, clearing the accumulated debris of a day's worth of thought and sensation and neural activity. What the morning brings is not simply a rested brain, but a cleaned one. A brain that has been maintained at the most fundamental physical level by the simple act of lying still in the dark and allowing sleep to do its work. The turtle knows nothing of glymphatic clearance, but its brain too rests in its own way. And in that rest, something is maintained that makes the next day of life possible. The slow, patient biological fact of an organism caring for itself simply by stopping for long enough, the relentless forward motion of being awake. Nothing is required now but this: the breath, the dark, the quiet weight of a body, finally completely at rest. And from here, the story barely needs to go anywhere at all, because where it is going is not a place exactly, but a quality, a texture of awareness so fine and so thin that it is nearly indistinguishable from what lies on the other side of it. The place where the turtle goes in its deepest winter, where the brain goes in its deepest night, where the boundary between the one who is resting and the rest itself grows so soft it simply ceases to hold. Aging in the biological sense is not simply the passage of time leaving its marks on a body. It is something more specific than that: a gradual accumulation of cellular damage, a slow erosion of the repair mechanisms that keep living systems running cleanly, a progressive drift away from the precise internal order that young cells maintain with such effortless efficiency. Researchers who study the biology of aging have identified several interlocking processes that appear to drive it: the shortening of telomeres, the protective caps on the ends of chromosomes that wear down with each cell division like the fraying tip of a shoelace that has been tied and untied too many times. The accumulation of senescent cells which have stopped dividing but have not died, and which release inflammatory signals that gradually alter the tissue environment around them. The declining efficiency of the cellular cleanup systems, the processes of autophagy and mitophagy that normally clear damaged proteins and dysfunctional cellular components before they accumulate into something more disruptive. All of this happens in every living body at some rate over some span of time. But the rate varies enormously, and turtles researchers have found occupy a genuinely remarkable position on the spectrum of how quickly these processes unfold. Some turtle species show what biologists call negligible senescence, a rate of aging so slow that it is at present almost immeasurable against the background noise of other biological variation. The Blanding's turtle, the painted turtle, certain species of box turtles studied in long-term field research, these animals show no statistically significant increase in mortality rate with advancing age, no measurable decline in reproductive success, no clear accumulation of the physical markers of aging that in most animals become increasingly visible as the years pass. They do not appear in the data to grow meaningfully older. They simply continue, year after year, decade after decade, maintaining their biology with a consistency that researchers describe as, in the context of the animal kingdom as a whole, genuinely unusual. What makes this possible is not fully understood. Scientists are still exploring the mechanisms, and the full picture remains genuinely open. But several factors have been identified as likely contributors. The metabolic rate plays a role. Slower metabolisms generate fewer of the reactive oxygen species that cause oxidative damage to cellular components, the molecular wear and tear that accumulates over time into the larger patterns of aging. The efficiency of certain cellular repair and antioxidant systems in turtles appears to be elevated relative to comparably sized animals with faster metabolisms. And the immune system of turtles shows a capacity for sustained function across very long lifespans that researchers are only beginning to characterize. There is also something in the relationship between body size and longevity that the turtle complicates in interesting ways. The general pattern across the animal kingdom, that larger animals tend to live longer than smaller ones, holds broadly, but with many exceptions, and turtles are among the most striking. A painted turtle, weighing perhaps a few hundred grams, can live for more than 30 years in the wild. A box turtle of similar size can live for well over a century under favorable conditions. The oldest verified tortoise on record lived past 190 years. These are lifespans that dwarf those of mammals, many times their size, and they suggest that something in the specific biology of the chelonian body, the particular combination of slow metabolism, efficient cellular maintenance, and the long evolutionary history of an animal that has had hundreds of millions of years to refine its own survival strategies, creates conditions that are genuinely, measurably conducive to longevity. Researchers who study longevity across species sometimes speak of a concept called the pace of life, the idea that different animals live at different metabolic speeds, and that these speeds correlate with how long a life tends to be. Fast-living animals, burning bright and brief, tend toward shorter lifespans. Slow-living ones, conserving energy, moving deliberately, asking less of their bodies per unit of time, tend toward longer ones. The turtle at the far slow end of this spectrum lives long, not despite its slowness, but in some important biological sense because of it. Slowness, it turns out, is not a failure of speed. It is its own form of optimization, its own answer to a different question than the one that speed is answering. And sitting with that, really sitting with it without rushing past it, there is something quietly worth feeling. The night has been long. The story has moved through many rooms, through the biology of a body built for patience, through the slow geography of sensing and remembering, and drifting through the invisible connections that hold living things within their worlds, through the rhythms that run beneath thought, and through the body's own calendar of rest and repair. And all of it has been circling in its own unhurried way around this same center, the question of what it means to live slowly, and what a slow life makes possible that a fast one cannot. Not a lesson, not a conclusion, just a quality of light that the whole story has been moving toward, the way a river moves towards something it cannot name, but has always known was there. Researchers who study what is sometimes called the restoration hypothesis in environmental psychology have found that natural environments and even representations of natural environments, images and sounds, and the felt sense of open living space produce measurable reductions in cognitive fatigue, in the mental strain of sustained directed attention, in the low-grade physiological arousal that accumulates through the day without necessarily being noticed until it is gone. The mind exposed to the kind of soft fractal complexity that natural environments provide, the irregular patterns of light through leaves, the non-repeating rhythms of moving water, the gentle unpredictability of wind through grass, enters a state of what researchers call effortless attention, a mode of awareness that is engaged but not strained, present but not focused, receptive without being vigilant. It is the mode of mind that a night like this invites, not trying to understand, not trying to hold anything, just present in the way that water is present in the glass that holds it fully there, perfectly still, without effort. The turtle does not know it is ancient. It does not carry the knowledge of its own longevity as a weight or a pride. It simply lives at the pace it was made to live within the conditions that are available to it without commentary. The 220 million years of its lineage exist in its bones and its shell and the slow chemistry of its blood, but they are not a story the turtle tells itself. They are simply what it is, quietly, completely, without remainder. And perhaps that is the most restful thing about the turtle finally. Not the slowness itself, though the slowness is real and measurable and biologically significant, but the absence of any gap between what the turtle is and how it lives, the complete, uncomplicated alignment of a creature with its own nature. No part of it straining toward a different speed, no part of it wishing the season were different, or the water warmer, or the day longer. Just this pond, just this mud, just this particular quality of darkness, just this single slow breath, and then the long quiet that follows. Researchers who study the neuroscience of self-compassion, the quality of relating to oneself with the same patience and acceptance one might extend to something genuinely valued, have found that it produces measurable changes in the nervous system. Reduced cortisol, reduced inflammatory markers, greater heart rate variability. The body held in its own kind, and patient attention moves physiologically toward the same restorative state that safety and comfort and the absence of threat produce. The body does not distinguish at the hormonal level between being held gently by someone else and being held gently by one's own quality of attention toward itself. Warmth is warmth. Safety is safety. The nervous system responds to both. And so perhaps the last scientific fact worth letting settle in this long and quiet night is simply this one, that rest is not a passive state. It is something the body actively moves into when the conditions are right, when the nervous system has received enough signals of safety and warmth and the absence of demand to release its habitual readiness. And those signals can come from the environment, from the dark and the cool and the weight of a body against a surface. They can come from the breath slowing on its own. They can come from the quality of attention itself, from the particular kind of softness that is possible in the late hours when the day has fully released its grip and nothing remains but this. The tide of melatonin is at its height somewhere in the dark of the body's own interior. The core temperature has settled toward its lowest point of the night. The breath is finding its own length, its own pace, without any particular supervision. And somewhere in the cold water of a quiet pond, a small ancient creature rests in the mud, with its heart marking slow time, its shell resting against the earth, its biology doing the patient and invisible work of maintenance and continuation that it has been doing uninterrupted for longer than there have been words for time. The same dark holds both of you. The same night, the same turning of the planet through its own slow orbit. There is something in that shared darkness that does not need to be named to be felt. Something that was here before the first turtle pulled itself onto the first warm shore, and will be here long after all the counting and the naming have grown quiet. You are already moving toward it, gently, without hurry, the way everything moves in the end that lasts.